With a conducive and well-equipped learning facilities, IKTBN Sepang has implemented a variety of curriculum activities that help to create the students' learning style and optimize their performance. In addition to the conducive training facilities, IKTBN Sepang also provides various other facilities such as accommodation, dining hall, Muslim prayer hall, and leisure center to ensure maximum comfort for the students. IKTBN Sepang always ensures its skills training is in line with the latest industrial needs by having smart partnerships and memorandum of understandings with various industries. These agreements are aiming towards equipping the students with the latest technology as well as to ensure their marketability to the industries upon completing the training at IKTBN Sepang. Driving the students towards innovation, generating idea, and creative thinking were part of essential aspects in IKTBN Sepang, with proper conduct of guidelines to enhance their quality and productivity. This is proven by various successful achievements of its students in innovation and skills competitions, either on national level or international level.
Banyak ilmu dan juga pengetahuan yang lahir daripada IKTBN Sepang ini telah diadaptasi dan diguna pakai sepanjang saya bekerja di bahagian industri terutamanya.
Jutaan terima kasih kepada pihak institusi kemahiran tinggi di negara Sepang kerana telah memberi peluang kepada saya untuk mempelajari pelbagai ilmu, kemahiran dan jati diri sehingga saya berjaya menamatkan pengajian saya dan berjaya menjawat jawatan yang baik di dalam kerjaya saya.
Sebanyak pembelajaran saya di IKTBN Sepang ini banyak membantu saya dalam melaksanakan tugas-tugas yang saya jawat sekarang sebagai maintenance di syarikat yang saya kerja sekarang.
Harapan dan doa saya semoga IKTBN Sepang akan terus cemerlang, melahirkan ramai pelajar mahir macam saya.
Saya rasa bertuah kerana berpeluang belajar di IKTBN Sepang di mana kesemua ilmu yang diperolehi banyak bantu dalam kerjaya saya hari ini. Terima kasih.
Pada pendapat saya, student-student IKTBN Sepang ini mempunyai disiplin dan semangat yang tinggi dalam bidang industri. Melalui latihan industri dengan syarikat kami iaitu AAZ Global dan Berhad, kami sentiasa memantau dari segi disiplin dan performance. Oleh itu, saya menyarankan kepada industri-industri luar supaya dapat memberi peluang kepada pelajar-pelajar ini dalam sektor industri.
Tahniah kepada Kementerian Belia dan Sukan, khususnya IKTBN Sepang, kerana berjaya melahirkan ramai tenaga mahir yang telah membantu dalam perkembangan pembangunan sektor industri negara seperti syarikat AAZ Global.
The successful national transformation towards a better future are depending on the excellency of leadership and harnessing human capital to its best, especially by the youth generation of Malaysia.
Terima kasih IKTBN Sepang.
IKTBN Sepang,
Hello, morning, Prof. Wan.
How are you doing?
Morning,
Nice
sir.
to meet you.
Nice to meet you. Sorry to take your time today.
That's perfect.
Okay, sir. Shall we start your presentation, or you want to start at 9 o'clock your time?
Yeah, okay. Do you want to wait for 5 more minutes or we just start now?
Yeah, after 5 minutes we start, sir.
Okay, perfect. No worries.
Okay, sir. Thank you. Apa sih?
Yes, sir.
Shall we start now? You can address Prof. Prof. What for start the presentation. Put me as a chairperson.
All right. Let us start now.
Yeah, sure. Please.
A very good morning to all of you. Hopefully, you all are doing good. My name is Muhammad Ismail from Plastic Production Technology at Institute Kemahiran Tinggi Belia Negara Sepang. Welcome back for second day of International Summit and Conference on Material Science, Nanotechnology and Biomanufacturing ISCMNB 2021. Thank you to each and every one of you for being here with us today. Without wasting time, let us welcome our first presenter for this morning, Prof. Juan from University of Mar del Plata, National Research Council, Argentina, will present about application of evolutionary algorithm for design full composite ultra lightweight pressure vessels for aerospace applications. I would like to invite Mr. Tina Karen to chair this session.
Thank you, MC today, Mr. Fizi. So before start our presentation, about Prof. Wan Moran, I like to introduce a bit. He's our executive plenary lecture. He's one of eminent authors and eminent speaker regarding the aerospace application. So without wasting his time, so I would like to invite Prof. Wan to start his presentation. Welcome, sir. Prof. Wan, are you there?
Can you hear me now?
Yes, sir. Yes, you may start, sir, your presentation, sir.
Okay, perfect.
Yeah.
Thanks for the introduction. Sorry, I was muted and I couldn't unmute myself.
Okay.
Yeah, this is the first time I use WebEx as a conference system. So
I see.
anyway,
But it's okay. Okay for you, is it?
yeah, it's perfect. I'm pretty much working. Everything is working now. So thanks everyone for attending my presentation. It's a pleasure for me to be invited for this conference. I hope you like the topic I have to present, and let's go through it. As it was said before, I'm going to talk about the application of evolutionary algorithms for designing full composite pressure vessels for aerospace applications. I work with a bunch of people. We are like 25 people in my group, but this particular topic I have been working with Dr. Rodriguez and engineer Churruca. So these two other people are working with me. First of all, just a little bit about my institute. We are located in Argentina. I'm located in a city called Mar del Plata, which is right by the coast. It's a really nice city. We have the sea, we have a nice shore. And within that city, we have the University of Mar del Plata, UNMDP, where we have our National Research Council Institute. This institute is focused on material science and technology. So this is kind of maybe for me it's a big institute, but for you it's small. I don't know the size of your institutes down there, but I seem for the introduction you presented 2 minutes ago that you are working in a huge institute. But here we have like 400 people. It's almost half of it about researchers. We have somehow 20% of professionals and technicians, and the rest of the people working there are PhD students or postdoctoral students. We have several divisions like polymer, ceramics, corrosion, metallurgy, welding and fractal mechanics, and surfaces and catalysts. Myself, I work for the composite structural groups. It's a research team of around 20-25 people, and we belong to polymer division. In that group, we are focused mainly on conducting basic and applied research in everything related to material science and technology. We are devoted to provide knowledge for industrial developments and applications, and we also try to keep innovation by bringing new students, both graduate and postgraduate students, and also we teach at the university at both graduate and postgraduate levels. So that's enough about me and the institution. Now, about the topic of this presentation, we developed this project together with the Aerospace Agency, our National Space Agency, which is its acronym is CONAE, C-O-N-A-E. And the idea is, although we are a country, a third world country, we are amongst one of the few in the world that are really thinking about launching things into space. We have been working on this project for over 10 years or 20 years. And here you can see in the map, Argentina is one of the few countries in the world that has is about to reach launching capability for satellites. Okay, this is our launcher. It's called Tronador. We are already in the second version, and we are planning the third version of it. This is, I do not work at CONAE. This is the space agency, but we work with them. So we have been collaborating in 3 different projects. We started working on prepreg materials for the craft nose to be able to withstand the heat and the pressure from the re-entrance to the atmosphere. Then later we started working on ablative composites for engine protection and thrust protection, and also some chemical system for fuel storage. And finally, for the last 5 years, we have been working on ultralight pressure vessels. There you can see that we call them type 5. This is a very specific subtype of pressure vessels. As you can see here, pressure vessels are used for storing pressurizing gases like helium, and our launcher uses 8 of these tanks. They have 200 liters of capacity, and they are arranged on the main frame of the unit, side by side, like this. You can see this guy sitting in the middle of the tanks. And from the beginning of the times, the storage of high pressure liquids and gases has been evolving from fully metallic to different stages. We start with type 1 cylinders, which were fully metallic, and they start evolving until type 5, which are only available for the US. There's no other agency that is using full composite tanks because of the challenge in the design. We are going to cover that later. But the main idea is that you want to reduce the weight. Just for having a rough estimation, every kilogram you want to put in space costs, like, as an average for all the space agencies in the world, $50,000 each kilogram. Each of these tanks weighs around 200 kilograms. So if you save weight by reducing the amount of metal and introduce composite materials or plastic materials, you can save tons of money in the launching, in each launching, okay? So the idea for this technology to evolve is to start wrapping the composite, the cylinder with carbon fiber composites at the first stage in the hoop direction, and then trying to cover all the different directions with different winding angles, okay? So our technology focuses on building filament winding pressure vessels, which are made by winding winding the carbon fiber tow outside of a mandrel. And you can see that you have two types of plies. You have hoop plies, which are oriented at 90 degrees, and helical plies, which are oriented at plus minus a random, not random, but an arbitrary angle in the body of the cylinder. Of course, this misalignment between the different layers conducts to a problem, which is the micro cracking. Micro cracking is what you see in the picture on the right, which are cracks that take place between two different layers. If you just imagine you are loading this composite on the right, can you see? Can you see the mouse pointer? I don't know, but anyway, here in the right, you can see this micro crack that is crossing from the top layer to the downmost layer. Every time you stress this composite, the misoriented or the not very well oriented layers start to crack. That cracking will lead to permeation on helium gases from the inside of the tank to the outside. And that's not good for our design. That's terrible. Okay. So one of the parameters we focus on is the microcracking resistance of the composite, of the layup or the laminate we are building. This is very well measured on a deformation versus crack density basis. And if you take two different materials and you plot their behavior, you can see that there are some materials that start cracking at very low deformations, like the orange one, and other materials that you can delay the micro cracking until a certain threshold. That threshold is about, in this case, 0.6% of deformation, and that will be the design limit for this material, okay? Of course, there are many ways of improving the matrix. We have been working on adding nanoscale reinforcements. This way, you can kind of glue the different layers together. We have tried with carbon nanotubes and halloysite nanotubes. We perform a TEM micrograph where you can see the dispersion. One of the greatest challenges is about dispersing the carbon nanotubes and the halloysite nanotubes. They tend to agglomerate a lot in the epoxy matrix. So we are also working on coating these nanotubes with to increase compatibility. For every matrix we formulate, we make a test. It's called the microcracking test or microcracking resistant test, where we can measure the crack density against the applied stress. You can see in the picture on the right, in the chart, that for the red dots, that's the neat matrix, and the green and the blue dots correspond to the reinforced matrices. So you can see that we can improve the stress at which the microcracking starts. So that's a topic. We also focus on this challenging design. But for us, for this presentation, we are working on the stacking sequence optimization by means of evolutionary algorithms. So we are going to leave the material properties fixed, although we keep changing them because we do a lot of research on that topic. But we are going to focus on the stacking sequence only. So our design requirements are the minimum weight. That's as much as you can improve the design to reduce the weight, you can maximize the payload of the rocket or of the launcher. So you can take bigger satellites or more satellites with the same amount of fuel because you reduce the weight of the tanks. We also need these tanks to withstand really high pressures. The operating pressure is about 400 megapascals, and you have to add all the safety factors to that. So we end up by designing 800 megapascal tanks, okay? And also we have to minimize the deformation to keep the gas permeation to the minimum. So we have found two slides before here that our threshold for permeation is 0.5%. So we are going to use that limit to keep all the deformations, all the strains below 0.5%. Sorry for that. So this is kind of a different problem because we have a special case here. Traditional approaches for designing composites involve netting analysis, which considers only the resistance of the fibers, and the matrix is adding no resistance to the composite. And then after you design by netting, you can perform finite element modeling. So in the best case, you can take up to 15 minutes only for computation for each stacking sequence. That's on a cluster computer, not on a what do you call that, in a desktop PC. It's on a cluster. It will take 15 minutes at least to test each stacking sequence. But here the problem is that the universe, the search universe, is almost infinite. Let's take, for example, a laminate with 50 layers and only considering angles between 0 and 90 degrees. You have zillions of combinations, so you cannot go for trial and error in that direction. So this is how, when we propose the use of genetic algorithms for finding an optimized solution, and then we follow that by a FEM or finite element verification. Okay. So we developed a layup design strategy with two objectives or consideration in mind. First of all, we have to minimize the weight together with minimizing the in-plane deformation. In-plane will be the directions 1 and 2 from the composite. We will discard the third component, which is number 3. So those are our design objectives, and we are going to make an abstraction from our real component. The real component is a pressure vessel fabricated by filament winding. We are going to assume a classic thin wall behavior, and once we do that, we can use the classical laminate theory, which is abbreviated as CLT. Once we do that, we can do an optimization. We are going to perform what is called an MOGA, which is multi-objective genetic optimization. And after that, we are going to verify our design by finite elements. Okay. So when you perform the thin wall assumption, you can only consider the cylinder part, not the domes. If you consider that the cylinder is a thin wall pressure vessel, you can estimate the stresses on both directions, on the X direction and the Y direction, Y being on the circumference and X being on the axis, and you can treat the composite as a plate. But the problem is that the CLT is not a single equation. You cannot derive or obtain the value of interest. So how do we do to get the best option? Okay, and this is where genetic algorithms come to our rescue. Genetic algorithms are a subset of the evolutionary algorithms. They are good for searching solutions among different possible solutions. They use different evolutionary mechanisms, including natural selection, reproduction, and mutation. And it may happen at some times that you miss the best solution, but you're guaranteed that you are going to find a good solution. Maybe you miss the best one, but your solution will be optimal. And optimality is defined mathematically, so it's okay with that. And these algorithms are very, very useful in problems where the search space is too big or they are too difficult to pose well by conventional techniques. Okay, so our genetic algorithm will be testing over 1,000 individuals per iteration. The individuals are the stacking sequences. You can see in different colors the different layers we use. We have to abstract that into what is called the ADN of each laminate, and we let these two laminates to reproduce and to bring to the world new kids. Those kids are again evaluated and re-allowed to reproduce. Okay, so that's called evolution for us. Our abstraction is like this. We have 6 steps. First of all, we create an initial random population. Here we define our ADN for each individual as the stacking sequence for the composite. The array of numbers represent each angle of the layup. They have to be between 0 and 90. And then we can add our manufacturing restrictions. Since this is done by filament winding, you have a minimum and a maximum angle, which are not 0, not 90. They are 3 degrees and 87 degrees. And also you are restricted by the dome profile you need to make. Your dome profile, which is the end bosses on the cylinder, needs to be designed in such a way that when you deposit the fibers, they do not slip on the profile. So all those manufacturing restrictions can be added into the genetic algorithm to get a good design. Then you perform a random population. You create 1,000 individuals with 50 layers, and you proceed to step number 2. On step number 2, which is called the fitness evaluation of individuals, you measure the response of each individual regarding the 2 objectives, okay? So each objective needs a method of evaluation. For the minimum weight, it's really easy because you can only count the number of active layers. If you know the thickness of each layer, you just count the active layers and you get the total weight for that guy. And for the minimum deformation, you can use our assumption of using the classical laminate theory, which is going to measure the maximum in-plane deformation. That way, you can see that each one of the individuals is a green dot on the chart. This chart is representing both objectives for our problem. On the x-axis, you have the objective 1, which is the minimum deformation, and the y-axis is the weight of the individual. So that's like a sketch of the full population of the generation 1, where you can locate each individual by its response to the system. There you can see that you have individuals with very high weight and high stiffness. This is because if you go down here, they are deformed. Their strengths are really small, so they are highly stiff. You can also have individuals with very low weight and low stiffness. These individuals are not good. These individuals are not good either because you are sacrificing one of the 2 objectives. Moreover, these individuals far way to the right and top of the chart, they have high weights and low stiffness. So those guys are not good at all. But in the frontier, on the red curve there, you can find a subset of optimal individuals. Those individuals are the ones that are closer to a point, sorry for that, to a point which is the intersection of the 2 axes, where you will have an individual that weighs nothing, that meaning it has no material, but it doesn't deform, it doesn't, it strains at 0. So that's impossible, that's a utopic point. So as long as much as the individuals get closer to that point, they are better. So after evaluating all your population, you have to perform a ranking of your individuals. You can order them by their distance to the 0. And then you select, this is natural selection. You say 10% of the best individuals are going to survive directly. They are going to pass straight to the next generation. So their ADN is translated directly to the new individual. You will allow 80% of the best individuals to cross over, that's to reproduce. So you are going to mix up the ADNs, which are the angles. You are going to mix up the ADNs of those guys to create new guys. Those new guys are totally different than their parents, but they have some information from them. So a good individual mixed with another good individual, it's probably going to behave well in the next generation, okay? And besides that, you will allow mutation. Mutation is random changes in some of the ADN variables or factors, which in nature occurs a lot, and you limit that to a certain amount of genes, like only a small percent of the genetic information can mutate. If you perform this operation repeatedly, you will start seeing that the optimum curve is going to get closer to the 0 point, the utopia point. You will never reach that point, but you are going to get closer to that point. You can see the red curve, which is the generation number 1, population number 1, population number 100 at population n. Okay? So this is going to be asymptotically reaching the optimum design for your pressure vessel. You define conversions of the system where the fitness of the system, of the overall population, remains invariable. That's where you stop your simulation. Once you stop your simulation, this is a real case scenario for our simulations. You have all the population and you select a subset of individuals, those who are close to your max deformation allowed, which is 0.5% or 5 times 10 minus 3, okay? So this way, we allowed ourselves to study more than 500,000 stacking sequences in 1 hour of computational time. And only a subset of those individuals were further evaluated by finite element method. That's almost impossible to be done by a direct approach, okay? Once we get the best individual from our evolution, we take it to a simple simulation, and we can see that the stresses and strains remain below 0.5%, and they are pretty much constant. That's not very normal in composite materials, especially these weird layups where you put different angles. And we're going to see how a real material behaves. But it's important to notice that our strains remain pretty much constant all over the thickness of the laminate, okay? Also, both the main stress is high enough, it's around 400 megapascals, and the transverse stress, which is sigma 22, remains below the matrix resistance. So this is a really good design. When you compare it to a non-optimized design, you can see that the stresses and the strains, they jump up and down in alternating layers. That's terrible for our designs, and it causes micro-cracking, delamination, premature cracking, and premature layer failure, okay? So, by using our optimization technique, we were able to reduce the thickness from the design, the handmade design by a really important set of engineers. They decided to use 5.55 millimeters, and we reduced it to 4.5 millimeters. That's like a 20% gain in weight for the composite, for the vessel, for each vessel. That being 20 kilograms per each vessel, and we have 8 of them. So we are saving like 1 tank among the 8 tanks we are taking to space, okay? Once we have the selected individual, we design the dome for that shape. And for doing that, we have to take into account the validated sequence. We have to design the dome in order to prevent the fibers to slip. We have to guarantee a geodesic winding. And we have to take into consideration also the polar thickening because of the agglomeration of the fibers on the polar radius. Okay, so these are our vessels designed by this technique. And once we have them, we can perform the full finite element modeling and use the Hashim failure criteria to identify the potential locations of failure. Of course, in these designs, the critical part is located on the top where the metallic emboss is placed in the interface between the metallic emboss and the recipient or the dome. You can see how it gets red in that part. So that will be the critical part or the critical point. After that, we went into the real world. We leave computers apart and we fabricated the tanks. We wind the tanks over soluble mandrels. So we do the winding. These are thermoset matrices. So we cure them in an oven and then we dissolve the mandrel. You can see some metallic axes there that are holding the embosses. Those are put there for connections for valves for filling it with helium later. We are actually not using helium at this stage. We are using water for hydraulic testing at 2 times the maximum operation pressure. That would be something around 800 megapascals. And you can see how it cracks in the region close to the emboss, in the interface between the 2 smallest angle layers. That's the weakest part of our design, but it goes beyond the needed pressure. These tanks fail at 810 megapascals, which is perfect for us. Okay. So I hope not to bother you anymore or to take your time. The concluding remarks here are that we designed a novel approach. We developed a novel approach for designing pressure vessels, combining the efficiency of evolutionary algorithms with the precision of finite element modeling. We could analyze and take into consideration a huge number of designs. This is almost impossible for normal procedures. The stacking sequence that we propose satisfies all the design requirements. We also fabricated the design and tested mechanically. And we compared it to a real tank we have that is actually being in use in the launcher, in the version 1 of the launcher. And we could make a significant weight reduction of actually it was 20%. Here, this is misspelled. So this is a huge accomplishment. What are we working now? We are working on another challenging design because we need to store hydrogen, which is much more dangerous, and it requires much more pressure. So this will extra limitate our design to 700 megapascals, which will require us to design for 1400 megapascals. Okay. Also, we keep studying how to increase the material resistance for microcracking by the addition of nanotubes and different nanofillers. And we are also working on the multi-scale modeling of the phenomena to see if we can predict the microcracking at different angles. And finally, we are working on the design of these materials for use at cryogenic temperatures and liquid oxygen compatibility. And I think that's it. Thank you a lot for your time, and I'll be glad if you have any comments or questions for me.
Thank you, Prof. Wan, for your wonderful talk today. And I think it's a very interesting topic about your aerospace. So I have one question before that. Okay, from the slide.
Yes.
Yeah, from the slide, you have to mention that's a problem in micro cracking, is it?
Yes.
Can you explain briefly why these things happen, micro cracking? Then how do you find out this micro cracking, and what is the main purpose of the micro cracking?
Okay, yeah, sure. Thanks for the question. Very interesting. The micro cracking happens because the material is anisotropic. It's not resisting with the same strength in different directions. So when you stress the material in one direction, the layers that are not very well oriented, but you needed them for the composite design, for the vessel design, but they are there. You need them, but they are misoriented. They suffer from the transverse cracking. Okay. And since we are trying to hold very small particles, actually helium atoms, they will permeate over each of the cracks and will go away from the container. So we don't want that. Okay.
Okay. Yes, sir. Any another question, sir? It's more to the tracking the issue of the problem that you face on your research. Is it any chemical modification can be done to solve this kind of the problems?
Yes, we have been studying with different formulations. We also formulate our own resins, and we have seen a great improvement on the micro cracking resistance by it may sound silly, but by adding reactive diluents. I don't know if I'm clear. They reduce the viscosity of the solution while it's curing. So while the network is forming, and since it's reactive, it makes a much better matrix, a much better network, okay? Polymer network. Okay, and it also gives much more mobility to our nanotubes, which are holding the matrix on the transfer direction, okay?
Okay, sir. Awesome. That's very clear. Thanks for your brief explanations about the microcracking and about your research. Okay, so now I'm open to the audience. They have any question that I want to ask our Prof. One is from Argentina. He spent his time today with us to share about his knowledge and is about the research. So I'm open now. So any questions from the audience, from the speakers, from the panels? Hi, sir. I think no more questions.
No more questions. No worries. That's
yeah. Thank you, sir. Thank you for your wonderful topic. It's a big interest about this because myself also I'm more to the polymer science. So it's quite interesting about your tracking. So thank you so much, sir, for your time. And
thanks a lot to you,
sir. Sorry, Prof. Karthik's here.
Hello, everybody.
Yeah, Prof. Karthik. Prof. Karthik also our executive plenary speaker. So, Prof. Karthik, anything you want to share or you want to discuss with Prof. One about his research?
Not right now. Because I was prepared. I had a very busy day, so I just joined a few minutes ago. But I'll check his research out on the web, and if I find something interesting, I'll contact him directly.
I see.
Right.
Yeah. Thank you, sir. Yeah.
Sure.
Okay, thank you.
Thank you so much, sir, Prof. One. So I'm passed back to our MC, Afizi. And Prof. Kaushik, are you there? So please on your unmute your mic, sir.
Yes. Yeah.
Prof. Kaushik is not feeling well today. So Prof. Kaushik, anything you want to ask with Prof. One about his research?
Yes. John, thank you very much for your nice presentation. You are working in carbon nanotube polymer composite. It's really very interesting to me. And of course, if we can join, if we can do some, the graphene polymer based any application. Graphene.
Yeah, we actually haven't. We are not including graphene at the moment because of the cost. And it's difficult to get in this pandemic situation here in Argentina. We are very far away from the world and our economics are really bad at this moment. So we did have a bunch of carbon nanotubes and halogen nanotubes, so we're using them, but it's in our list of topics, not at the moment.
Okay, very good. No problem, please. I really appreciate your nice presentation. Okay, thank you.
Thank you, Prof. Kaushik and Prof. One. So I'm Afizi. You ready for next presenter, Dr. Laili? Dr. Laili is here, our another executive plenary speaker. So Afizi can appoint Prof. Kaushik as a chairperson for Dr. Laili. You may start from Afizi, you may start now.
Thank you, Prof. Juan, for the wonderful explanation, and Mr. Tinakaran for chair this session. We move on the next presenter, Prof. Nur Hidayatul Laili from University Malaya, Malaysia, to give a talk about fabrication of hybrid curcumin captured cool nanoparticle reduce graphene oxide as potential antioxidant and colon cancer cytotoxic agent. I would like to invite Prof. Kaushik to chair this session.
Sure. So I would like to request Professor Laili, please join us and share your slide for presentation.
Thank you, Prof. Kaushik. Okay, so I try to share my slides. Is it clear? Okay, you guys, can you see my slide?
Still loading. Yeah, can visible, man. Can visible.
Yes. Okay. So first of all, and good morning to everyone. Okay, thank you for inviting me. I consider this as a sharing sessions, some input or findings from my small laboratories at which is Nanotechnology and Catalysis Center, located at the University Malaya. So for today, I will talk on the how the biotechnology combination of the nanomaterials and biotechnology and how it can significantly give a benefit for the new trend on the cancer treatment. Okay, so for today's talk, it's about as I mentioned by the Mr. Hafizi, is on the fabrication of the hybrid curcumin cat gold nanoparticles, which means we do the synergetic hybrid or combinations of the gold nanoparticles and the curcumin, okay, and be supported with the graphene oxides, okay, and this combination of this ternary chain materials have potential application as the antioxidants, and it can be used further for the colon cancer. So how it happened? So we will go through for this presentation. Okay. As you know, cancer. So cancer is a global problem. Okay, so it was a second leading cause of death. Okay, so we consider that every 6 deaths in 2018 was due to the cancer, and it's not missing for the Malaysians. The same problem, the same scenario also happened in Malaysians, whereby cancer is the first leading deaths in Malaysians. Okay, and it recorded that almost 100,000 new cases has been diagnosed annually, okay, from the period of 2020 to 2016. And for this project or for this study, we are focused on the colon cancer. And why colon cancer? So colon cancer is the second highest cancer type in the male, and a second highest cancer type for the female in the Malaysian populations after the breast cancer. And the sad situation is majority of the colon cancer has been diagnosed at the advanced stage. It's not at the third or fourth stage. Okay, so it's at the critical stage. Okay, so this is quite sad, and that's why we are motivated to come out with the new technology combination of the nanotechnology and biotechnology, how we can help to do some prevention or treatments for the colon cancer. Okay, for the conventional therapy, most probably for colon cancer, they are focused for the chemotherapy, which by we are using the for clinical and the surgery. But the limitation of this series of therapy is on the selectivity. Because this type of therapy, even though it is record a good effective method to cure the cancer, but it still has low selectivity. It means not only the cancer cell has been treated or has been destroyed or has been dead in during the therapies, but also it involves the cells. Okay, so we have problem on the selectivity actions. Okay, for the normal cell cancer, and we also have the side effect, which is this is quite difficult for the for example for the chemotherapy for the drug to be released from our body after the treatment. Okay, so it will give a side impact due to the long resistance of the drug in the body. So around and the most important part that around 50% of colon cancer patients they have a developed recurrent disease, means after the treatments, after they go through for the any treatment of the chemo or radio surgery or phototherapies, they have a chances for the cancer cells to be reoccurrence. Okay. So we are looking for the next generation for the cancer treatments. Okay, and the reason for the next generation of cancer treatment, we focus to the more safe, which means we secure the normal cell or the health cells. Only we focus on the death of the cancer cells and have the multi-targeted modalities, which means that it can be the technology that can be used cancer treatments, but with the specific targets, cancer cells. Okay, so this include for the cancer immunotherapy, which is we increase the immune system of the patient. Okay, then this can be done with the we provide more the white blood cells in the patient bodies. Okay, to include their immune system, so the body can self fight the cancer. And the second one on the gene therapy, whereby we introduce healthy genes, okay, around the cancer cell. So it will be the self-killing of the cancer cell. And the last, these two that have been received extensive focus on the nanotechnology and plant-based drug. For the nanotechnology, we are using the nanomaterial or nanostructural materials, okay, to be drug deliveries for the cancer cells. Okay, so examples that are commonly used is the iron oxide in the nanotube or iron oxide in nanoclusters. Then that can be induced a self-apoptosis, which is that can have a self-death. Cancer death. Okay, so the second one is the plant-based drug. Okay, the most common one is the okay, but they have some limitation for this two technology. Even though it shows some promising properties for the for as a cytotoxic agent for the cancer, but they have some limitation for these two. So for today, we will come out with the one solutions with a combination of these two technology with nanotechnology and plant-based drug technologies for the better cancer treatment application. The very foundation of cancer start from the diagnosis. For example, for the for diagnosis, prevention until the treatments. Okay, so for cancer diagnosis start from the censoring. Okay, prevention, how the nanotechnology can help to stop the cancer growth, and the treatment, how the cancer cell can be cured by the treatments. Okay, so this is the statement by the National Cancer Institute in 2004. Okay, and the nanomedicine type, normally they include the nanotherapeutic agents, which is we use a nano-size drugs, the phototherapy, which is we use a nanomaterial, which is highly sensitive under the light irradiations, and it can be killed. The cancer cell can be killed. Okay, once it will be introduced by the light at a certain wavelength, and combination of the therapy, which is the combination of the conventional chemotherapy with the phototherapy. Okay, and for example, if the phototherapy will combine with the chemotherapy, so there will be a dynamic treatment for the cancer treatment. So for the nanotechnologies used in the cancer therapy, there are graphene, okay, as I mentioned by Prof. Kausi, Prof. Joan talk, the graphene is one of the material that get attention for the cancer treatment application. Okay, so why graphene? Graphene is due to the structure. We see the structure of graphene itself because it's the honeycomb structure, sp2 carbons. So it is considered as the thinnest or the smallest carbon-based material in the world, but with the high strength properties. Okay, so and the graphene itself, it has the oxygen functionalities on the surface. So it's easy for the further functionalization of the graphene. So it can be attached with the other type of material, for example, polymers, okay, or carbon-based CNT, or we can decorate the surface of the graphene itself based on our objective or intentions. Okay, so it have the high surface area, of course, because it has only a carbon chain itself, and that's why due to the high surface area, we can have the maximum drug loading on the graphene surface. So it's easy for fabrication. So normally it just involve one step synthesis process from the raw material, which is graphite, and only an acidic medium is needed to do the oxidation from the graphite to the graphene oxide. And a good thing and why people are more interested on the graphene is due to, for the cancer treatment especially, due to the cellular interactions and uptake mechanism, which means that graphene can have the good interactions with our cell body, and we have the uptake mechanism, which is they have a good fashion on how they how they load and unload the drugs. Okay, drug here is for the to treat the cancer, and the combination of the graphene and gold recently also received more intention. Okay, why gold? Okay, gold nanoparticles. So gold is has been long time ago been used to treat not only a cancer but many type of diseases. Okay, so why gold? The first reason is highly stable due to their zero oxidation state. So it's totally chemical inert. Okay, so it is biocompatibility. So this is what we need. Okay, especially for the cancer treatment, for in vivo, for especially for the in vivo testings. Okay, we use it in our where we use in our human bodies. So we need it in our body, and also it can be released from our body with the normal digestion process. So it has the anti-cancer properties because it have the due to the stability and the zero oxidation properties. So it can induce the direct oxidation necessities to kill the cancer cells. Okay, and easily functionalize. So we don't have a problem in fit of the gold nanoparticle is due to their plasmonic effect. So it can be high, can be change. It can be changed the reactive or non-reactive properties. Okay, so this is important. Okay, so thermal therapy application for cancer. So the next the title. So we have use three materials, okay, 18 somethings, okay. So it had been used before, okay, but not as the treatment, but the cancer for the cancer treatments, okay. So I give the benefit of the curcumin itself. Okay, it have a good anti-cancer activities. So it can degrade the tumor, okay, growth factor receptor. So and induce the autophagy, okay, in the cell cycle. This means that it can induce the cell death of the cancer, okay, and it have a highly reactive oxidation species modulation, which means that due to its functional group of the phenolic and enolic, it can inhibit the free radicals in our for the cancer treatment application. Okay, so study shows that steady increase in the use of complementary and alternative medicine among the cancer patients. Okay, so this showed some increase for the biological product. So people now looking to the organic materials, okay, okay, for the to treat different type of the disease. For example, curcumin, it can be it has been used to treat the arthritis and HIV infection, and it shows some positive results from that. But why curcumin does didn't get attention for the cancer treatment is due to some limitations. Okay, people doesn't use it for the human clinical trial because it's the chemopreventive actions. So as I mentioned, it's not used for to treat the cancer, but it's more to the preventions. Okay, and it has a low solubility due to the hydrophobic nature. The curcumin itself, it have a phenolic group with two benzyl group, okay, linked with the methoxy groups with and phenolic and enolic groups. So all these structures are hydrophobic. So it is not suitable to be used in our body because it's cannot be digested in our system. Okay, so they have the low bioavailability and solubility and uptake. Okay, so that's why the curcumin still now are not using as a um, uh, drugs for the cancer treatments. So we have these three materials, which is have their own limitations and also which have their own advantages. To synergetic combine these three materials concept of the structure analysis relationships. Okay, so this is the design for purpose, which means for the conventional nanocomposite synthesis approach, they're using a trial and error approach. Okay, where we start with the material synthesis and we do the performance assessment or the characterization or analysis of the materials. And then if there's material success or material can pass through all the characterization or analysis, so we can apply for the application. This is what previously done. But now we do for the design for purpose approach, which means that every single material or functional group that we intend to be incorporated in the system must have a specific reason or must have a specific justifications, and each justification or the reason must meet well with the objective or with the target. of the applications. So the design for purpose approach start from the problem definition. As I mentioned, phase 3 material, the curcumin, graphene oxide, and also the gold nanoparticle. They have advantages to be to in the cancer treatment, but they also have some limitation, and how we can overcome the limitation of each material by this combination or by this hybrid. Okay, so we start with the problem definition, the conceptual design, how we design the structure. Okay, and the synthesis method is a selected synthesis method. Okay, so and at the end we will do the characterizations or analysis on the performance assessment of the material obtained. Okay, so in our SLR design, we consider about the suitable platform. Okay, the drug choice. The suitable platform here is the graphic, right? The drug choice. Okay, the synthesis, how the hybridization method can be happen, and then the characterization, what characterization technique that can answer the problem statement of the research, and the suitable cancer model, what type of model cancer cell, and cytosolic activity and mode of action. Okay, so this is the material designs that for these research projects. So we have the design for purpose approach that suitable platform for drug of choice. Okay, for the gold nanoparticles. So gold nanoparticles will act as a spacer to prevent aggregation. So this aggregation comes from the graphene oxide, because as mentioned, the graphene oxide is the most thinnest or smallest material in the world. Okay, so it's contained of the planar honeycomb structure of carbon. So and it have the hydroxy group, the oxygen functionality group that make it easy to be aggregate. Okay, so that's why in order to prevent the aggregation of the graphene oxide, we need the gold nanoparticles. Okay, the gold nanoparticle will be a spacer. Okay, or we build a linker between the graphene oxide. Okay, to make sure that it has a stable honeycomb structure. Okay, and then it also a well-established biocompatibility, so it can be it's safe for our digestion systems. Okay, so it have it can be released by our body. Okay, with a natural way. It also the anti-cancer property. Okay, due to the innate chemical properties and easy to functionalize. So the limitation of graphene oxide itself has been overcome by the gold nanoparticles. And why we choose the graphene, the high surface area for efficient functionality of drug loading. So we want a maximum drug loading. Okay, that's why graphene is selected due to the high surface area. Okay, and this is easy fabrication for easy synthesis process. And the most important thing, it has a good cellular interaction, which means that it can be localized inside our inside the cancer cells, okay, by itself, and do the uptake or uploading or loading or uploading of the drug by itself. Okay, but they have the limitation, as I mentioned, for the cell aggregation tendency, and graphene is not biocompatible. Okay, so we need some further functionalization to make the graphene compatible, okay, with the human body. So it can be used for the analysis. For the curcumin, so it have the anti-cancer properties. As mentioned, due to the enolic and phenolic structures of the curcumin, so it has a tendency to inhibit the free radicals that normally have in the cancer cell environment. Okay, so it has a reducing agent effective in nanosynthesis. So curcumin also is a good reducing agent to reduce from during the synthesis process, to reduce from the graphene oxide to the reduced graphene oxide. So we use curcumin. So in this case, curcumin not only as an agent, but it is during the synthesis process. So it acts as a reducing agent as well as a stabilizer for the whole system. Okay. So but curcumin itself, it had a low cellular uptake. Okay, and that's why it doesn't have a good interactions with the cancer cell. And then due to the hydrophobic properties of itself, so it's not compatible with our body system. Okay, so that's why combination of these three materials can overcome the limitation of each. And here, as mentioned, curcumin is a reducing agent as well as the anti-cancer drug. So unlike the previous report, so why these studies are considered advanced as referred to the as compared to the previous report, because here graphene-based composite synthesized by the green methods. Okay, so that majority show inconsistent use for the human cancer and normal cell lines. So they have the inconsistent result and they are not used for the human cancer and the normal cell lines. Okay, and the lack of selectivity. That's why the system itself is well functioned for the cancer treatment. For it being toxic to the cancer treatment, it can kill the cancer treatment. But in the same time, it's also toxic to the normal cell. So they have the lack of selectivity here and the lack of cellular uptake study. So means that it cannot be localized in the cancer cell itself, the system. So combination of the curcumin to this system is in the previous report, they normally include a two-step chemical reaction. So it will start with the producing or synthesizing of the graphene-based composite and followed by the attachment of the curcumin. And this will give a toxic impurity due to these two-step chemical reaction. And it shows the low selectivity toward the attachment of curcumin on the graphene-based composite. And no proof for cellular interactions, okay, or mechanism of action, how the system can be interact with the cellular wall or cellular wall of the cancer cell and normal cell. So altogether might contribute to indeterminate conclusion and hinder the further development. So that here is the some example, and while people using the graphene-based composite for the cancer treatment. So they are using the apply for the breast, for example, the breast cancer, combination of the curcumin and the graphene oxide. Okay, and they are using for the in vitro applications. Okay, so there are also some but that's why we highlight the advantages of our research, which is for the current studies. Okay, the first row. Okay, so we are using the graphene based composites with the green synthesis agent, which is the curcumin, and we're using for the two type of the colon cancer, which is the first one, the HT26, is the mild cancer type, and the second one, the SW948, is the aggressive cancer type, which is cannot be cured by the conventional chemotherapy. Okay, and we show the high selectivity for these two. Okay, so we then is due to this positive result will be presented later in the result in discussion of PA. Okay, the objective of this study, okay, we want to synthesize, okay, the gold graphene curcumin composite using the one-pot green hybridization method. What is the one-pot synthesis process? As mentioned previously, okay, most of the previous studies, they're using two steps of the synthesis process. Okay, first they produce or they synthesize the graphene composite, and then followed by the attachment or functionalization of the curcumin. But in this study, we use a one-pot green. one pot means that one step, one batch synthesis process of the composite, and to optimize the chemical interactions of the material involved. Okay? And we want to make sure that only with the this synthesis process will produce a minimum toxic material as a subproduct. Okay, and then once we get the composite material, so we would like to verify the antioxidant. So these antioxidant activities of the synthesized nanocomposite using DPPH assay. So antioxidant activity will give us how good the attachment and how many the volume of the component on the surface of the graphene gold. Then we want to evaluate the in vitro cancer toxicity and selectivity and effect of curcumin nanocomposite on the colon cancer and also the normal cell lines. So here the selectivity, how the cancer, how the composites, okay, how our composite can be a cancer prevention, normal cancer, but to be a cancer toxic to the to be a toxicity to the cancer cell. And lastly, if possible, of mode of actions by the oxidative stress and cellular uptake based assay. And this will be done by the electron microscope, and we will see how the action, how the interaction with the cellular, how it can be localized in the scan the cell, and how it can be induce the apoptosis or the cell death, okay, during the cancer treatment application. So the study will have two stages. Okay, the first stage is on the qualitative of the structure analysis, synthesis design, and we go for the synthesis. Okay, this is synthesis. Which everything will be in one step. Okay, and do the calculation to confirm the structures, the properties of the composite, and we do the antioxidant activities. The stage 2 or more for the cancer treatment application, where we will study about the toxic of the and to prevent how it can be prevented and the repair mechanisms after the cancer treatment process, and the selectivity of the system, how it can diagnose which one is the cancer cell, which one is the normal cells, and we go to the mode of action or the optosis, okay, the pathway of the cancer death and cellular uptake, and the oxidative stress profile. Okay, for the first stage, the nanocomposite green synthesis. So it will happen in one step. Okay, so we start with the oxidations of the graphite. We use the improved Hammer method, which is much more better than the conventional Hammer method due to the toxicity of the subproduct. Okay, by here we add some combination of the sulfuric and sulfuric acid, and to stop the reaction using the potassium permanganate. I think everyone everyone has done a study on the graphene. They are familiar with this Hammer method. Okay, so after that, in order to make sure that the graphene itself have a stable one layer of the honeycomb, so sonication will be done for 30 minutes, okay, before we introduce the gold salt, okay, and then curcumin at the pH of 11. Okay, the sampling level will be compared. So we will not only produce the our composite system, which is we call CAG, but we will compare the properties of CAG, our own composite, with the traditional graphene gold nanoparticles. Okay, so and previously people are using the sodium citrate but there are some problem on the sodium citrate due to the toxicity, and this will be compared with our system and the graphene oxide itself, between the graphene oxide without any functionalizations. Okay, the characterization we carry out for the electron microscope, the TEM, high resolution TEM. We want to see how uniform the structure of the gold nanoparticle. Because here we introduce the new type of the capping agent, which is the curcumin. So we want to see how the curcumin can produce a nano distribution of the gold nano on top of graphene oxides, and the structure change and functionalization will be analyzed further in the Raman spectroscopy, the SIR and SRD for the carcinogenity. And the next the solution is as I mentioned. So graphene have the curcumin itself, they have a problem on the dispersion for the hydrophilic medium because of the hydrophobic properties. So this study will see how we change the properties of curcumin and how it can be stable and soluble inside the different test medium. Okay, we study about then it will support with the zeta potential and the SN result. And for the last one, the antioxidants. So we study the phenolic content. So the phenolic content will determine on the how active our material towards the antioxidant towards free radical. So protein phenolic content, TPC and DPPH analysis will be carried out. So for the stage 2, which is we focus on the cancer applications. So this is the method how the analysis will be done. Okay, the composite, the CAD composite will be dispersed in the medium, and this medium will be stored up to 40 degrees Celsius. And here we use 3 types of colon cancer. The normal colon cancer, CCD841, okay, and the colon cancer, we have 2 types of the colon cancer, which is HT29, is very friendly or can be treated under the chemotherapy, and SW9S48, which is for the chemotherapy. And we will see and compare how our system, how our treatment are better than the chemotherapy treatments. Okay, so all these 3 types of the colon cancer cell will be further analyzed toward the selectivity index. Okay, and the mode of action. Okay, so here is some analysis that will be carried out. Okay, to confirm the selectivity and to confirm how well our composite system with the cellular of the cells. Okay, and all these reaction will be captured or will be furthered by the TEM, the electron microscope, the transmission electron microscope. Okay, so now time for result and discussions. So how this material can be fabricated. So the graphene oxide itself has the oxygen functionality group, which is the negative charge. Okay, and the gold nanoparticle, our room, so 3+ is the cation. So due to the different charge of these 2 materials, so they can have a good electrostatic interactions, and it will have a good distribution of the gold on the graphene sheets. Okay, so there are some during the synthesis process, there are some aging timings around 2 to 3 hours. Okay, in order to ensure that the gold are well distributed on the graphene before we introduce the curcumin. Okay, so the curcumin will help, okay, on the reducing of the graphenes to be the reduced graphene oxide. Okay, and reduction of the gold nano of the aurum anion to the gold to the aero nanoparticle, which is the gold nanoparticles, nucleations, growth, and the maturations. So this is happened in the pH, pKa of the analic and phenolic structure of the curcumin, which is at the pH 9.2. So this is okay. So in order to confirm that the gold graphene gold has been functionalized homogeneously on the graphene sheet with the capping of the curcumin. So this analysis is carried out. TEM, Raman, FTIR, and SRD. For the TEM, the electron microscope analysis, so we can see the sp2 functionalized of graphene oxide group for all these three sample. The graphene oxide, our composite CAG, and the composite, the graphene oxide composite synthesized with the citric acid. So, but what is special about our composite is on the distributions of the gold for the sample of CAG and the TEM compare with the RGO nanoparticle. So you can see a single particle distribution of the gold with the average particle size of 50 nanometer. So as compared to the previous studies with the citric acid capping agent, so they have a subagglomeration of the gold nanoparticles. So we can confirm here that the curcumin act as a better capping agent and reducing agent for the gold graphene oxide composite as compared to the citric acid. Okay, for the Raman spectroscopy, so we can see that the for the G band and D band, okay, so they have some reductions on the G band and D band, G band of the our composite as compared to the conventional graphene of nanoparticle reduction on the oxygen functionality on the sp2 of the graphene oxide. So we can confirm that all the oxygen functionality of the graphene has been successfully functionalized by the gold nanoparticles in our composite as compared to the conventional method using the citric acid. Okay, and from the FTIR, we confirm that the insertions or the functionalization of the curcumin in the composite system. Okay, so we have the spectrum of the curcumin itself without functionalization, and the fingerprint of the curcumin presents in our composite parts. Okay, for the SRD, so we confirm that the sp2 or the carbon functionality or the graphene at 001 planar. Okay, so this one shows some reductions. The same result with the Raman, which is the oxygen functionality of the graphene oxide itself has been occupied, completely occupied with the gold nanoparticle. And the gold nanoparticle characteristic peak for the SRD for the composite has been presented in the planar of 111 and in the red colors of the planars. Okay, so it confirms the presence of the gold as well as the reductions on the numbers of oxygen functionality of the graphene oxide due to the surface functionality with the graphene and with the curcumin and the gold nanoparticle. Okay, so gold itself, they have a good light sensitivity property, which is we call the plasmonic effect. Okay, so we do the UV-Vis, okay, UV-Vis analysis to confirm that the gold has been functionalized on the on the graphene oxide, okay, to produce our composite system. So structures with the gold nanoparticles due to this surface plasmoresonance effects, okay, shift, okay, then it confirm the presence of the gold on the graphene nanosheets. And the result has been supported with the TGA, thermogrammetry analysis. When we see the multi-stage curve, okay, of the reduced structure for the curcumin functionalization, whereby it increased the thermal stability of the graphite oxide material. So all these characterizations together, we confirm on the formations of the composite with the graphene oxide as a support material functionalized with the curcumin, functionalized with the gold nanoparticle capped with the curcumin compound. Okay, so I mentioned previously, one limitation of the curcumin is due to the hydrophobic nature. Okay, so due to the phenolic and enolic group, and also due to the benzene structure group. So it's a totally hydrophobic material. So it can be seen for this wettability analysis. Okay, so it's totally hydrophobic material. But once we do the we functionalize with the graphene oxide, which is the high lipophilic materials. So the wettability will increase, and it more to the become more hydrophilic material. They are suitable to be used in our body system. Okay, so this is how the okay. Now our composite system are hydrophilic, okay, and it can be dissolved in the human body. But how the dispersion stability? So we do the zeta potential analysis, and it shows that the composite come out and the composite give a value more than 20 MV, which is stable all over the period of time. Okay, we do for the 1 hour, 12 hours, 24 hours. As you can see from these pictures, even after 24 hours, our composite, which is CAG, are highly stable as compared to the curcumin CR sample, which has already do some sedimentations on the bottom of the flask as compared to CAG. And the stability is consistent with the with the composite produced by the conventional method of the nitric acids. Okay, so the size of due to these changes on the hydrophilic to the hydrophobic, so the size of our composite, okay, is considerably higher when we do the analysis as compared to the graphene oxide. Okay. And for the antioxidant activities, okay, we can see that once we increase the concentration of the curcumin, okay, in our composite, the antioxidant activity will be increased simultaneously. Okay, so it's due to the inhibition of the free radical. So in the DPPHP analysis, okay, so the composite itself, so it has so addition of the curcumin, so we introduce about 50%, 30% to 50% of free radical inhibition as compared to the conventional graphene oxide. Okay, this is curcumin itself. They have the phenolic group here and the enolic group that act for the free radical inhibitions. Okay. And this picture captures how, when we introduce our composite or hybrid system of the graphene oxide and golds and the curcumin, so how it interact with our cell lines. Okay, so we can see here for the normal which is the cancer cell that are a good response to the chemotherapy treatment. So compared to the SW948, which is resistant to the cancer cells, so you can see that additions when we increase the amount of composite, so the more cellulose shrinkage and profilin invasion will be performed. So means that the cancer cell react well with our composite system, even though for the SW948, which is resistant to the chemotherapy treatments. Okay, and this one will be increased significantly with the concentration of the CAG. But when we compare for the normal cells, for which is in 841, the inhibition or the visibility is quite linear. Means that this composite will not attack or will not induce any opportunity or cell death to the normal cell. It's only focused on the cancer cell. So that's why we can include that it have the high selectivity. Okay, so it only at the concentration up to 1000 microgram per ml or ppm. So it can inhibit almost half of 50% in the cancer cell, but maintain which is zero mode of actions. Can when we introduce the composite, okay, so we have several here for from A to D for the H29 cancer cells, for E and F for the more aggressive cancer cells. So you can see that both of the cancer cells, even the mild or the aggressive cancer cells, they show the similar mode of actions. Okay, how the nucleus change. Okay, the nucleus change with the chromatic condensations, and then it have a good cellular uptake of the composite. Okay, and it and the membrane building before the apoptosis body will be happen at the end of the cancer treatment process. So both of the sample treatments, okay, for the both of the cancer cells, the aggressive and the normal cancer cells, effects on the level of ROS, which is the reactive oxygen species, which is when we increase the concentration of the composite, so the possibility for them to to kill the reactive oxygen species is getting higher. So this is the pathway how they react from the cancer cells from the cellular uptake, and then do the ROS and how the and end up with the apoptosis process, the cell death process. Okay, as a conclusion, we produce a novel nanocomposite that combine not only a well-designed nanocomposite template system, but it use a green one-pot method, which is we have minimized the toxicity and the sub-product produced during the synthesis process, and it have a good antioxidativities for the for our composite as compared to the traditional nanocomposite, and high selectivity toward the cancer cell and maintains the normal cells, okay, and a good uptake and antioxidant modulating pathway, including apoptosis, which means that our composite system can induce a self-destructive mechanism to by the direct oxidation for the cancer cell. Okay, project actually this project has been ended by last year, but we're looking forward for more studies that include a different type of cancer cell lines. As I mentioned, even though the colon cancer is the main problem for the male patients, but we focus more on the we would like to try this system for the breast cancers, because the breast cancer there are more issues that need to be overcome before it can be tested by our system. Okay, and it's the first cancer killing in formulations for female. Okay, and we want to do the next in vivo drug delivery stage, okay, including how to structure development, coating to control how we can fashion the drug release of the system with the detailed kinetics. So and by that we can control how the releasing profile of the drug at the high selectivity of the treatment. And we want to study other possible mode of actions or mechanism that will possible for the our composite treatment in the cancer cell. So this is the paper that we managed to produce throughout the research project. Okay, some of them focus on the synthesis of the one-pot synthesis process, and some focus on the cancer cell applications for the our system. So the research team are based on, and this project cannot be done without the support from the research team in the which is the Nanotechnology and Catalysis Center, Universiti Malaya, and we are collaborate with Faculty of Pharmacy, Universiti Malaya, in part of the cancer treatment and how the MOA, the mode of actions, how the cellular interactions happen, and what type of the cancer cell lines are suitable for this study. All these one have been provided or which is justified by the Faculty of Pharmacy, Universiti Malaya. So some brief introduction about the NanoCat, where the research has been carried out. So it's a part of the Institute of Advanced Study, Faculty of Institute of Advanced Study in Universiti Malaya, that focus on the research for the nanotechnology and catalysis. So we working on the material design, the smart materials, chemical catalyst, energy and environmental catalysis. So all these will be used a nanomaterial to capture or to deliver the objective of the study. So for the catalyst, we're working for the nanocatalyst, the magnetic materials, the semiconductor oxide, carbon nitride, smart nanomaterial. Also, we're working for the composite coatings, chemical synthesis, energy additive, and environment mitigation to treat the different type of the pollutants. So for that, I would like to thank you, everyone. And for the further detail, you might contact me at this email address. Thank you.
Thank you very much, Dr. Laili, for your presentation. Very, very detailed, ma'am, your presentation. So, yeah, I have thank you so much. And I have one question.
Because I thought that I have a long time, so I make it detailed.
Oh, no problem, no issue on that. Can you move to slide 26?
Which one? 26.
It's about shrinkage. Yeah, number 26. Yeah, 26.
This one.
Based on the scanning electron microscopy, is it? Okay. Why these things happen between six pictures there? Why the last one is more the porosity is happened? Yeah. Why, ma'am?
Okay, so this one, the first one, we have two concentration of the graphene here, which is 62 microgram per ml and 250 microgram per ml, which will increase the concentration of when we increase the concentration of the composites, so it will induce more cellular shrinkage of the cancer cell. Okay, so they have a difference. So if your question is about why HT229 and SW948 give a different characteristic or different morphology, so because the HT29 is much more responsive as compared to the SW948 for the chemotherapy. But in our situation, both give a same response towards the composite. So it's a good news for the one that the one who looking for the alternative alternative of the cancer treatment as compared which is currently is more on the chemotherapy. So this one will be a good alternative. So it shows that even we use organic material, which is the curcumin, which is everyone in the kitchen they have the curcumin for their cooking, but who believe that this material can treat well the cancer cell as compared to the chemical drug. So
Yeah. So thank you, Doctor. But there's sorry, another question is regarding the few articles. I went through few articles. Now they are do some research on the graphene. Graphene can be modified as a blood cell or stem cell. Is it any possible, Doctor, for modification on graphene as a stem cell or blood cell?
Okay, graphite. You mean how we can functionalize the graphite with the stem cell? So we can. Okay, now we see what the application. What the justification of using graphite here, because graphite here is support materials or loading materials. Okay, so graphite, why we use a graphite as a loading material is due to the size itself, or the size, the surface size itself, so you can give the high surface area, and due to the functionality, the functionality structure of itself, which is the oxygen functionality. Okay, so refer back to your question. So it's possible because we have the functionality that easy to be linked or easy to be functionalized with the different type of the functional group in the stem cell, and also it can carry the maximum loading of the stem cell due to its high surface area. So it's possible to be used, but you need to find the application because the graphite is the hydrophilic material. Okay, it is the lipophilic material, hydrophilic. So we can see how we need to study more on the surface of the stem cell. It's not, maybe it's not directly attached with the stem cell with the graphite oxide, but we need another material as a linker. For example, or any compound to be linked between the stem cells and the graphene oxide.
Okay. Thank you so much, Doctor. So
if I can ask you what your research background?
No, actually I'm
so
not.
I think you're.
But I'm quite interested about this.
If you can share with me what?
No, I'm actually quite interested about the cancer cells and everything. So yeah, it's quite nice, ma'am. Your presentation, very detailed, very brief explanations. So I'm passed back to Prof. Kaushik. He's a chairperson for this session. Prof. Kaushik.
Hi, Dr. Laili. Thank you for your nice presentation. I'm really curious for your I'm really curious for your work based on, did you really synthesize for the graphene dots via green synthesis? I've seen in some of your slides.
Graphene dot, we didn't do any functionality on graphene dot of the, okay, so we go back to the, this one. Okay, so we didn't add any elements or doping any element on the surface of the graphene.
Yeah. This is purely synthesized via green synthesis, right?
Yes. Which one, Prof?
I'm just talking about TEM figure 2.
Figure 2. Okay, TEM analysis. Figure 2. Okay, yes.
Is it graphene dot?
No, the dot or the dot there is a gold nanoparticles because the size is the 50 nanometer, Prof. Okay, so it's big enough for the doping elements.
Okay.
So it's a
So
gold
my question,
nanoparticle, Prof.
you dope gold nanoparticle with graphene, right?
Yeah, we functionalize the gold nanoparticles on the graphene.
And you apply for the biogenic application, let's say for antimicrobial activities like that, anti-cancer
Yes,
activities.
but this one with the curcumin, the addition of curcumin. Previously, people are using the graphene gold is without the any plant-based materials. So for the novelty of this study, we introduced the curcumin as the anti-cancer or antioxidant compound for the to be potential to be applied in the cancer treatment.
Very good. And I really appreciate your nice presentation regarding, because I have one work on based on gold nanoparticle. So same activities, but this work really very appreciating to all of us, and I'm really grateful to join in our conference as a executive plenary speaker. So okay, go ahead, please. Thank you so much.
Yeah, Prof. Thank you. Okay, Prof. Thank you. So maybe after this we can have some further discussion on the because you're also using the graphene also.
So in future,
so if also, Prof, can I ask what application of your graphene also?
Hello.
Hello.
Yes. What's your question?
Yeah. Application for your graphene oxide composite, Prof.
I applied for the switchable device. And also biogenic applications. I will discuss with you through email. Okay. And of course, in future, of course, in future, I can do some collaboration with you, University of Malaya. Okay.
Yeah. I also did some graphene oxide go for the biosensor, Prof. Just for your info. It can be related to your studies.
Sure. Thank you.
Okay, sure.
Thank you so much.
Thank you. Thank you.
Thank you so much, Prof. Kaushik and Dr. Laili. Yes. Afizi, shall we move to next presenter, Dr.
Another 30 minutes.
Dr. Indu for the next presenter.
All right. Thank you, Prof. Nohidayatul, for the interesting presentation, and Prof. Kaushik for chair this session. We move on the next presenter, Dr. Indu Elizabeth from CSIR National Aerospace Laboratories, India, to give a lecture about multi-wallet carbon nanotubes or PDMS-based wearable sensor for human motion monitoring. I would like to invite Mr. Tinakaran to chair this session.
Thank you so much, Mr. Hafiz. So, good morning, Dr. Indu.
Good morning, sir.
10 o'clock.
Yeah.
So, are you fine?
Yeah.
Okay, Dr. Indu. So we will start your presentation. So as we know that Dr. Indu is our keynote lecturer from National Aerospace Laboratories, India, and she's going to talk about multi-wall carbon nanotube PDMS-based wearable sensor for human motion monitoring. Without any wasting the time, I would like to invite Dr. Indu to start a presentation.
Okay, sir. I'll share my slides. So is my slide visible?
Yeah, ma'am, visible is audible. Yeah, you can proceed now.
Okay. Thank you, sir. And good morning to all. I'm Dr. Indu, and I'm working in the Surface Engineering Division of CSIR National Aerospace Laboratories. And today, the topic of my talk would be multi-wall carbon nanotube PDMS-based wearable sensors for human motion monitoring. Before going into the presentation, I would like to give a brief introduction about the institute in which I am working. And I work with the CSIR National Aerospace Laboratories, which is the pioneers in India's civil aircraft design and development. Recently, in the 31st of March 2021, we have rolled out the two-seater Abinsho aircraft, Hansa NG. It is an all-composite aircraft and is first of its kind in the country. And another technology which is being worked upon is the Saras Mk2. That is a 19-seater aircraft and is promoted as the indigenous option for government's Udan scheme. And I work with the Surface Engineering Division, that is SCD division, and SCD has been pursuing research in surface modification technologies for aerospace, societal, and engineering applications. The current research areas in SCD division includes energy, sensors, corrosion technology, material characterization, etc. And I have joined CSIR NAL only in the month of October 2020, prior to which I was working with CSIR National Physical Laboratory, New Delhi. And my research interests include real-time corrosion sensors for aircraft, carbon-based sensors for like monitoring human motion, and also lithium and sodium-ion batteries, in which I have done my PhD. And coming to the topic of the day, that is wearable sensors for human motion monitoring. As we all know, the advent of sensors in the application world has revolutionized the quality of human life. Earlier, what it took hours or hours to study or monitor, now it can be addressed within a minute or seconds with the help of sensors. But monitoring of the psychological parameters of a human being is one of the most important application of sensors because it can help in developing a model for human behavior. And the schematic here shows a monitoring system for sensing the physiological parameters like respiratory rate and heart rate of a human being by connecting wearable sensors on different parts of the human body. And the data from these sensors can be transmitted through the cloud through any information gateway. And this is a quick and efficient system because any abnormality in the data which is detected can generate a notification to the healthcare or the family members, so appropriate measures can be taken and the life of the person can be saved. Also, these wearable sensors have drawn much attention due to their potential application in wearable electronics, e-skin, and in artificial intelligence. The sensors can be broadly divided into flexible and non-flexible sensors. The non-flexible sensors have been developed earlier, and among which the silicon-based sensors are the most common ones. The conventional metal or semiconductor-based these non-flexible sensors, they have restricted application mainly because of their poor sensitivity. They have a gauge factor around 2, and also they have a limited monitoring ranges, reducing their full range healthcare monitoring application. And also they have added disadvantages like stiffness, due to which they cannot be mounted on the human body for flexible applications. And coming to the flexible sensors, they are defined as flexible devices which can transduce physical or environmental stimuli into a detectable signal. Particularly, these flexible sensors can be mounted on a human skin or a human clothing, and it can be used for continuously monitoring the subtle or large human motion or physiological activities like pulse, ECG, or temperature changes. And towards these applications, the flexible sensors should have certain important characteristics like they should have high sensitivity, they should be highly flexible, and good stretchability and fast response time. Also, they should be biocompatible and they should be highly stable. And if you're considering a flexible sensor mainly consists of the electrode for taking the data outside, and the active component, and a flexible substrate. And in particular, the selection of the active component plays an important role in dominating the performance of the sensor. And to date, various materials have been used as active materials, mainly carbon nanotubes, graphene, carbon black, conductive polymers, metal nanoparticles or nanowires, and semiconductors. And among these, metal nanoparticles-based sensors, flexible sensors, are used for high sensitivity applications, but they have a limitation. They have very small sensing ranges. Similarly, the conductive-based polymers, because of their poor stability, it is very difficult to work with them, and so they are also limited in applications. In contrast to these, the carbon-based materials are the most commonly investigated materials due to their remarkable mechanical, electrical, and thermal properties. And also they can provide like high sensitivity, and they also exhibit high flexibility when infused in a flexible substrate. Also, we can have a desired configuration and good stability for these carbon-based sensors. And towards the right side, like we can see like what are the applications of these carbon-based materials for different flexible sensors. And in our study, like we have used multi-walled carbon nanotube as an active material for making the flexible wearable sensors for human motion monitoring. As we all know, CNDs are very considered as sheets of graphite which is rolled into a cylinder. And the most important peculiarity of the CND is that they possess a high aspect ratio, which potentially enables the CNDs to form internally highly conductive networks. And these networks break down when they are stretched and eventually reconstruct when the strain is released, leading to a significant change in the electrical resistance. That means it has a piezoelectric behavior in itself. And there have been several studies for the use of on the versatility of CNT-based flexible sensors for human motion detection. And as already told, that for the wearable sensors, the actual requirement is that the sensor should have a high sensitivity, which demands like large structural deformation of the material when it is stretched or like when it is strained, so that there is a significant change in the electrical signal which can be detected. And also another requirement is the good stretchability. That means we need to have a flexible elastomer or a matrix material which is structurally intact, and it can withstand large deformation without any breakage. And the first thing which comes into our mind is like when we are using CND is like the random distribution of CND in a polymer matrix. But the random distribution of CND has certain problems, like it has poor partial dispersion of CNDs in the polymers is like difficult. Therefore, it can lead to poor processability, and there is inferior flexible properties. But if we are using aligned CNTs, it can provide a better conductive pathway, which could increase the sensitivity of the sensor. And also, the conductivity of the CNDs is highly dependent upon the orientation and the length of the structure, so which can provide a better conductive path, which could further increase the sensitivity of the sensor. So in our studies, we will be going with a vertically aligned carbon nanotube. The vertically aligned carbon nanotubes, which we have used, is grown by CVD process. And in order to fix which polymer metals has to be used, like we have studied with 3 different polymers. One is the PDMS, that is polydimethylene siloxane, and polyurethane and epoxy polymers. And in this case, we'll go into the details. And in this case, the CND forest has been infused in these 3 different polymers. The SEM image here shows the VSCND forest. We can see like a properly aligned carbon nanotube here. And the principle behind this sensing mechanism is a piezoresistivity. Like as we can see, the vertically aligned carbon nanotube forest is infused between the polymer layers. So whenever a compressive load or a stress is applied, the carbon nanotubes get buckled up or they get bent and they come close to each other. Thereby the resistance will decrease because there is a proper conductive path now. So upon the increase in the compressive load, the resistance increases. That means the sensing principle is a piezoresistivity here, and which the change in resistance is monitored to get the desired output. And in the SEM images here shows the some of different, when the nanocomposites were made with the PDMS sample, that is a B image, and then with the PU, and then with the epoxy. Here we can see that for the PDMS sample, the polymer has infused properly into the CND forest, and we can have a very smooth surface here. But for the other two, there are certain porosity which is being observed. Then we have done the IV measurements. In the IV measurements, we can see that both the PDMS VSCND and the PU VSCND, they both show an ohmic behavior. That means there is a conductive path in the sample. That is mainly because of the incorporation of the VSCND in the polymer. But for the epoxy, like there is, it doesn't show epoxy-based VSCND nanocomposite. It doesn't show an ohmic behavior, or that means there is no conductive path. The behavior is same as the epoxy polymer itself. And then we have done the compressive stress strain cycles. In this case also we can see that for the PU based and the PDMS based, the the strain level went up to 50%, and there are two main regions in this stress strain curve. One is up to the 10%, in which the stress is increasing like linearly with the strain, and this is called the elastic region. And after 10%, the strain is not increasing linearly but at a very slow level as compared to the strain. This is mainly the plastic region, and in both PU and PDMS we can see these both. But in the epoxy nano composite, it was seen that the composite failed even at a strain level of 4%. And also when the VSCND was incorporated into these polymers, there was an increase in the compressive strength of these polymers, mainly for the PDMS and the PU composite. For the PDMS composite, there was an increase about 447% as compared to the VSCND forest alone, and about 834% like as compared to the polymer alone. So there was an increase in the compressive strength also. But for the epoxy, there was no particular change in the conductivity nor in the strength. So we are dropping the epoxy studies here, and then we are comparing the PDMS and the PU composites for carrying out the further studies. And here we have studied the piezoresistive response of the PDMS VSCND and PU VSCND, and this was done by loading these samples with calibrated force, the calibrated weights in different ranges, and the force was given like a loading of 2 Newton up to 20 Newton, and then for 5 Newton up to 10 Newton up to 50 Newton, and with a duration of 20 Newton for up to 150 Newton in both these cases. And if we can see that when the force is increasing, the resistance is decreasing. That is, the change in resistance is also increasing. R0 is the resistance. Like here we have given the change in resistance, relative change in resistance, where R0 is the resistance of the sample when no load is applied, and R is the resistance when we are applying a particular load. So in both these cases, there is it shows a piezoelectric behavior on the application of load. And also the studies were done with an applied strain up to 50%. And in this case, this is the A sample is the PDMS VSCND sample, in which we can see that the change in resistance went up to 2. But in the PU VSCND sample, the change in resistance was only up to 0.6. That means the PDMS VSCND sample have a better or higher sensitivity as compared to the PU sample. Also, this resistive behavior was done studied for up to a number of 20 cycles, in which we loaded the sample up to 50% strain and then unloaded it. And in the PDMS VSCND sample, that is A figure here, we can see that even after the 20 loading unloading cycles, the change in resistance is almost the same. But for the PU sample, there is a degradation in the change in resistance. That means that the sample is not very stable. And so for the further of our studies, we go with the PDMS VSCND nanocomposite. So coming to the conclusion that PDMS is a better polymer for being used in the VSCND forest, then we have developed a VSCND PDMS sensor, which is based on thin film and which can be used for human motion monitoring. And this sensor has a sensing range of from 0.004% to 30%, and also it has a very small response time of 12 milliseconds. And we have checked the cycling stability up to 10,000 cycles, and it exhibited a very high gauge factor of 6,436 at 30% strain level. And as already told, this thin film sensor, the VSCND which was used in this was fabricated by using CVD process, and then we infiltrated PDMS into it. And here are the SEM images. First is the VSCND, and then we can see the SEM images in which the VSCND forest is infiltrated with the PDMS polymer. And this is the sensor which we have fabricated. And from these Raman images of the VSCND before the infiltration of the PDMS and after infiltration, you can see that the D by G ratio is almost the same. That means the PDMS polymer has not done any damage to the CND forest. And coming to the studies, like we have done the tensile stress strain studies for these thin film sample for about 1,000 cycles. And we can see that from the first cycle to the 1,000 cycle, the sample behaved the same. That means it is highly stable and highly stable up to 30% strain. But when it was exposed to a higher strain of like above 50%, up to 50%, as seen from the SEM images, we can see that there is a creation of a crack inside this as seen. So like the better range for this sample was found to be like below 30%. And from these Raman studies, also we can see that there is no major like shift after the after going for 10,000 cycles of stress strain. That means the sample is stable up to 30% strain. And up to 30% strain is more than enough for monitoring the human motion, because even the vigorous human motion like will come under a strain level of 30%. And here, as I have already told, like when we exposed these to a strain level of up to 30%, then we observed that the gauge factor was coming up to 6,436. And in this graph, we can see that there are mainly three regions. One is up to 10%, where the change in resistance is mainly due to the tunneling effect. In this region, the VSCNDs are densely packed, and then there is a high conductive path. And when it is stretched beyond like 10% up to 20%, there is a discontinuation in the path, and the resistance starts increasing. And when it is stretched beyond that, there is a far more like disconnection, and therefore the resistance increases to very high values, and then therefore we are having a very high gauge factor. And these CNTs were also the stability of these CNTs were tested up to a 30% strain level for 10,000 cycles, and we can see that it is the almost stable for 10,000 like cycles, showing that this sensor can be used for a long time in the actual application. And then we also calculated the dynamic response time of these sensors by using a tapping action. And in this, we can find that the response time is only 12 milliseconds. It is able to, and the recovery time is 19 milliseconds, which is very low. So it is an ultra fast sensor. And when we have actually used these sensors for monitoring the subtle motion, one is like we have used it for monitoring the pulse of a person, in which the sensor was like wrapped on the wrist of the person, and then we measured the pulse, and the pulse was measured for a person of age 29 and weight around 68 kgs. So like we could get the pulse of like 72 before like any exercise. So this is actually the normal pulse, and we could even distinguish between the systolic and the diastolic peak in these from these the data which was observed. And when like after exercise we monitored the pulse, we got a raised pulse, and the pulse was about 88. And also like we like fix the sensor on the forehead to know whether there is any frowning, whether frowning of the like forehead can be detected. In that case also we could get a signal. And also while gulping, like we put the sensor on the throat, and while gulping water we could also detect a signal. And another thing which we had done was like we pasted the sensor on a balloon, and then we inflated the balloon in different levels. This can be compared to a kind of breathing, like whether it can detect our breathing or not. So in this case also we could see that at different level of like inflation, like the sensor is able to give different outputs. And apart from this human subtle motion, we also exhibited the sensor to vigorous human motions like wrist bending or finger bending. In this, like the wrist bending, the sensor was placed on the wrist, and then it was moved up and down. And so we could get an output, a distinctive output like this. And in the case of finger bending, the sensor was placed. And here we can see that at different angles of finger bending, the relative resistance change is different. That means even the sensor is even able to detect a very small change in the like actions. And also like then we exhibited the sensors to mechanical stimuli detection. The sensor was bended and the sensor was stretched. In all these cases, the sensor is giving a distinctive output. Here also the twisting of the sensor was done, in which like we could get a output like this. So from these, like it can be observed that the sensor can be used for monitoring any kind of human motion, from the subtle human motion like pulse to vigorous human motions like bending, twisting, like twisting, etc. Here I have added two videos. One is like to just show you how the sensor works. One is the rolling of these sensors, in which we can see that when the sensor is rolled, like we get an output like this. And one is a wrist bending, in which like we can see like how the sensor works when the wrist is bended. Then apart from this, like vertically aligned carbon nanotube, because like we have also tried with a multi-wall carbon nanotube, bucky paper, PDMS flexible wearable sensors. Actually, vertically aligned carbon nanotube, to make this alignment, it is actually very difficult. So we have tried another method, one that is using the bucky paper. Bucky paper, as all of you know, it is a sheet of like carbon nanotube, and it can be easily made by using the vacuum filtration technique. The carbon nanotube can be dispersed in ethylene glycol, and it can be filtered through using a vacuum filtration technique through a filter paper. And upon drying, the bucky paper can be peeled off. And what we did was that we have sandwiched the bucky paper between two PDMS layers. And this is the synthesized bucky paper PDMS sensor. And from these like some images, we can see that this is the bucky paper layer, and these are the PDMS layer, like which is keeping it sandwiched. And from the inside this, we can see that the PDMS has infused inside the pores of the bucky paper also. This is the bucky paper image. And this bucky paper based PDMS CND sensor, this is also like, this is a recent work which we have been carried out, and this has also been proven to like monitor different human motions like finger bending, wrist bending, walk, even walking, and then like other mechanical stimuli like bending, twisting, rolling, tapping, etc. And this doesn't have a much high gauge factor as a vertically aligned carbon nanotube. It has a gauge factor around 2000, and we have also done the cycling studies up to 10,000 cycles. And here, like I have shown few images in which like one is the like on finger we have pasted and we have bended it. Here also it is able to detect at different angles of finger bending. This is for the wrist bending, and then we have placed it on our shoes, and then like we have walked whether to monitor the signal or not. In this case also, like we are able to monitor the human movement. And another one is for the mechanical stimuli, in which like we have rolled and twisted, and then this was for tapping. In this also, everywhere like these sensors are able to give a distinctive like response. So this can be actually used for monitoring human motion. Other than that, it can be used as e-skin also for applications for robots or in artificial intelligence. Then coming to the conclusion of my presentation, as already told, conventional metal-based or semiconductor-based like non-flexible sensors, they have restricted application in human motion monitoring because of their low sensitivity and limited monitoring ranges. But if we are using wearable sensors, they have excellent sensitivity, high extensive sensing range, good stretchability, fast response, and reproducibility, and they are highly desirable to emulate the multimodal sensing attributes of human skin with full range healthcare monitoring. And we have fabricated the VACND PDMS thin film sensor, which can detect like even subtle to vigorous human motion in the range of 0.004% to 30% strain deformation. And this sensor has it is ultra high sensitive, and have exceptionally fast recovery response time of 12 milliseconds, and it is durable up to 10,000 cycles. And also the multi-wall carbon nanotube bucky paper PDMS sensor, which is a little more cost-effective sensor, but which has a gauge factor about 2000, is also a promising sensor. And this is the sensor which we will be working on in the future. And thank you all. And I would like to acknowledge my HOD, Dr. Harish Barshilia, and Sharon J. Paul, she is my PhD student, and Dr. Bipin Gupta, my colleague, was in CSIR NPL. And also this work was done under the startup research grant like from Government of India for the development of carbon-based force sensors for artificial intelligence and biomedical applications. Thank you all for listening to me. Any questions?
Thank you, Dr. Indu,
for
your presenting this topic. Is about the sensors, motion sensors will apply for the human. Is it the research is already done or still in the prototype?
Sir, actually, VACNT, this sensor is like almost we have developed the sensor. And this sensor would be actually used for monitoring the Parkinson's disease. Like in India, we have an Institute of Parkinson's. They have actually asked for these sensors. So we will be delivering it to them. And so they will be actually checking it on the patients.
Awesome. Awesome. Madam, I have one question.
Yeah.
Regarding the polymer you chose, PDMS, PU, and epoxy, is it? Is it any particular reason why you choose these three materials for your research?
Sir, actually, like it was based only upon the literature survey. So from the literature survey, we could actually see that like there have been a lot of research on these polymers, and for a flexible sensor, there has to be a certain range of like mechanical strength and flexibility. Based upon that, only we have selected these. And in these, actually, we could find out that for our application, the PDMS is like better.
I see. So and then you have to mention that in your research, there's no response in the epoxy material. Is it why these things happen?
Sir, actually, epoxy, what had happened is like when we made the sample, it was very stiff. Like when we applied a compressive strength, it is only like getting cracked. There is no particular change. That means like because of the epoxy, it like properties only because of the stiffness only, it is not able to like respond to the stress. So there should be some elastic behavior.
I see. Thank you so much, ma'am, for your explanation.
Thank you,
so now I'm open to our other presenter or speaker. Any questions? Any discussion you want to share with Dr. Indu? Anyone there? Any questions? Okay, Dr. Indu, I think no question there.
Yes, sir.
I don't know, Prokosi is not feeling well. I don't know he's online or not. But very, very interesting topic, ma'am. Is it a move to it's about Industrial Revolutions 4.0, right? So you can so that's a very interesting topic about this. So thank you so much, ma'am, for your sharing session and as a keynote lecture for our conference, this conference, and support this conference. And thank you so much, ma'am.
Okay. Thank you, sir. Thank you.
Okay, Fizi, we can move to another presenter, but I think Dr. Rao is not around. Is it Dr. Abu Imran is here? Are you online, Dr. Abu?
Yes, I am online.
Doctor, okay. Sorry to bothering you. Actually, suppose your presentation yesterday, is it? You not joined?
Yeah. Actually, I was trying to enter the hall room. I tried and I waited for several hours only, but several hours I waited there, but I could not find any link how to enter like hall 2. So that is why I quitted, and you know that I am now in USA.
Oh, I see.
Now in USA, and there was some time difference also. So then I just quit my waiting.
No problem, sir.
Yeah,
no problem. So, are you available to share your slide? To share your lecture now? Possible?
Right now, I have to just I need to modify. I'm not prepared actually.
Okay.
I need time to get prepared the slides.
Yeah. Okay. So actually, we have two slot is free. Actually, after Dr. Indu, suppose Dr. Rao have to present, but is not unable to join. He text to me unable to join. And another doctor from Bangladesh also, Dr. Subaratra Sareka, he also unable to join. So we have two slots free before the break. If you not,
I thought I missed the opportunity. That's why. Actually, I was waiting yesterday. So then when I I could not enter the room, I
Oh, I
thought
see.
maybe I missed that opportunity. So
Okay, no
I had
problem, sir.
yeah, I just like a 30 minutes or 1 hour. I need to like modify my slide or
No
arrange.
problem, sir. Maybe we
Yeah,
can
so
start 2 o'clock Malaysian time. So now it's
okay.
11:20 in Malaysia morning.
Mhm.
So we will
Okay.
start at 2 o'clock Malaysian time.
Okay.
So maybe you can join after 2 o'clock. I will WhatsApp. You don't have WhatsApp number, is it? You don't have, is it?
I have WhatsApp number.
You have WhatsApp number, okay. So then you just chat to me, sir. You send your number. Then I will propose the time that you can present this afternoon session. In chat room,
Yeah.
you can WhatsApp your number, your WhatsApp number. Then I will text to you.
Okay, I'll send you my WhatsApp number and I will talk to you later. Maybe.
Okay, sir. Thank you so much. Thank you so much.
Okay. Okay. Thank you.
Okay, busy. So I think we don't have any presenter after Dr. Indu. So we all move to all one. So after afternoon session, we have Dr. Prabhu, Dr. Saguntala, Dr. Vengadeshan, and Dr. Sudhakar, and including Dr. Abu will give a talk today, afternoon session. So morning session, Dr. Rao and Dr. Subertra unable to join due to they have another task. They are unable to join. So I will move all the presenter to all one. So we can join all one. So I will do that. Okay. Okay, busy.
Okay. Yeah, sure.
Okay. Okay. I will move everyone into all one.
Human being almost 160 pounds. So we wanted this composite to actually hold up this biting force. So it even increased the wear resistance and polishing ability of the material. So this is how the nanotechnology was advantageous in the incorporation of other nano fillers in composites. So this led to the discovery of nano composites. These nanocomposites had something called as the resin matrix as well as the nanoparticles. This was basically invented based on the bottoms-up approach of nanotechnology, where smaller particles were joined together to form the bulk material. And in that, two types of nanofillers were used, that is nanomeric particles and nanoclusters. Nanomeric particles were of the size of 20 to 75 nanometers, and nanoclusters were of size almost 2 to 20 nanometers. materials. So these are some of the nanoparticles or nanofillers that were used. And as we all know, nowadays titanium oxide was also used in conjunction for the discovery of the nanocomposites. So in the market, we have already quite a lot of nanocomposite materials present. So let us look into the advantages of these nanocomposites. These nanocomposites enhance the polishability of the resin, and high filler loading and the aesthetic appeal. Superior fractional strength was also seen, and they reduce the polymerization shrinkage, leading to less staining of the tooth. That means it maintained the white color throughout the lifetime. Superior hardness, translucency, and even aesthetic appeal was seen. So, in comparison to the same material which was having macro particles, macro or micro, the nanoparticles can be easily arranged in number of packing configuration due to their high surface to core ratio, making them easily manipulated and utilized in various applications. Within this context, there is a high surface to core ratio, making them because of the surface charge. So there are certain benefits of these nanoparticles in composites. So these nanoparticles helped in the surface charging ability, then degree of hydrophobicity. The ratio of the surface area to biofilm mass had the ability of the particles to absorb or to collect on the surface of the biofilm could be changed. Now, even though there were so many things, even though the nanocomposites gave so many advantages, still, we wanted to bring about many more desirable qualities of this composite. That is, the newer material features included remineralization ability of the material, reducing the polymerization shrinkage, and getting the antibacterial property, increasing the biocompatibility of these materials, increasing the shelf life, lowering the shrinkage, excellent aesthetics, as well as the wear resistance. So today, my talk will be in and around how we have brought about antibacterial property in this composite. So before we go into the antibacterial property, let us look into the mechanism of action of antibacterial agents that we are looking into. So these are some of the antibacterial mechanism of action of certain antibacterial agents which are used in composite. First is the cell membrane adhesion and the membrane damage, where the positively charged ions actually attach to the negatively charged ions of the bacteria and leads to killing of the bacteria. Then there is loss of protein stability, and these nanoparticles will penetrate and accumulate inside the cell and the nucleus, giving rise to bactericidal action. And the mitochondrial and endoplasmic reticulum dysfunction is seen. There is alteration in the cell signaling, that is RNA signaling is disturbed, and there is breakage of the DNA replication. And of course, lastly, there is generation of oxidative oxidase enzymes, which will lead to the oxidative stress and thus killing of the bacteria. These are some of the mechanisms of action of antibacterial agents that are seen. But however, it depends on the type of antibacterial agent that we use in composite. Now let us look into the types of different antibacterial agents that are used. Though there are many antibacterial agents present in our field, but there are only certain materials which actually could be incorporated into composites. These are some of the antibacterial agents which were incorporated into the composite to bring about the antibacterial activity. They have a major role in dentistry since ages. So now let us look into detail about each of this component. First is the fluoride. As we all know, fluoride is already a very old material used in dentistry. It is used in almost all oral hygiene aids, that is toothpaste, mouthwashes, dental floss, or even toothpicks. The main antibacterial action of this fluoride is that it acts against Streptococcus mutans to inhibit the demineralization process, promotes the remineralization by forming the fluorapatite crystal. That is, it hardens the tooth structure to fight against the bacteria. And when this fluoride is put into the composite, it is released in exchange of reaction with the water diffusion. However, plain fluoride cannot be used in this composite. So there were different filler types, that is strontium fluoride, then quaternary ammonium fluoride, or tertiary zirconium fluoride, chelate. The main advantage of this fluoride in addition to composite was that when fluoride was added into composite, it did not change the mechanical as well as the physical properties. But still, when plain fluoride was used into composite, it had its own drawbacks. That is, it created void. As soon as the fluoride was released, it created voids in the composite. And then the amount of fluoride which was released in the composite was not equivalent, or it was less than the already materials present in the market, that is glass ionomer cements. So now let us look into nano fluoride. That is, how did this nanotechnology help fluoride in the retainment of the material. Now, these are some of the studies which have been done in relation to nanotechnology with fluoride. First is the use of quaternary ammonium compounds with nanoparticles of calcium fluoride. When these two combinations were added into composite, it gave about a strong antibacterial action with increased ion releasing capabilities, and it did not compromise the mechanical properties, as well as it avoided the biofilm formation on these two, and of course the colony forming units of the bacteria was less. Then there was something called as rechargeable calcium fluoride. This rechargeable calcium fluoride, when was added to the composite in the form of nanotechnology, nanofibers or nanoparticles, it gave long-term remineralization ability. Antibacterial properties were also promising to inhibit the caries lesion. When you talk about recharging ability, it means that there is a material inside your tooth which has rechargeable calcium fluoride. It had the ability to take up fluorides which were incorporated. That means you have a filling in your mouth, and if you brush or if you use any oral hygiene aid with fluoride, that fluoride could be taken up by the material. So that is how it gets recharged. Next is the use of chlorhexidine, calcium phosphate, and as well as calcium fluoride, where the mixture of all these elements in the composite also helped in the reduction of biofilm formation, acid production, and colony forming units, and the metabolic activity of bacteria, thus leading to enhanced anti-caries action. Next, let us go into the next component, that is zinc oxide. Zinc oxide is also used in dentistry as a temporary filling and even in gingival dressings. In composites, it avoided the biofilm formation, and it was used in plain form. Zinc oxide did not have any different type of filler components, and only 1% of mass was enough to bring about the desired abilities, that it did not change the mechanical properties of composite. The antibacterial action was by cutting the supply of the membranes of the bacteria and metabolism of sugars in the biofilm, and generating active oxygen species such as hydrogen peroxide, which inhibited the growth, disrupted the enzyme systems, and displaced the magnesium ions essential for the enzymic activity of the dental biofilm. Now let us look into the nanoparticles of this zinc oxide when incorporated nanocomposite. So in composites, when these nanoparticles were added, it exhibited excellent compatibility and enhanced the antibacterial effect against the Streptococcus mutans. And then there were certain other studies where the zinc oxide was added with titanium oxide and even silver nanoparticles, which to achieve potent antibacterial activities without compromising the bond strength. However, even though zinc oxide nanoparticles were good when they were incorporated in composite, but their role was much more enhanced when they were used with other fields of dentistry, that is the coatings of implants or denture bases, or when they were used as scaffolds in bone tissue engineering. Though zinc oxide has its main advantage, but was mainly used in other aspects of dentistry. So let us look into something called as chlorhexidine. Chlorhexidine again is used in dentistry in toothpaste, mouthwashes, and usually to treat periolesion as disinfectant, as an antiseptic. The bacterial action is in two ways. That is, at lower concentration, it has a bacteriostatic action, and at higher concentration, it acted as a bactericidal. When added into composite, it was based on water sorption ability of the composites. The filler types of chlorhexidine was chlorhexidine dihydrochloride, chlorhexidine gluconate, and chlorhexidine diacetate. Again, the addition of chlorhexidine did not change the mechanical as well as the physical properties. However, there was still some drawbacks seen, that is, there was antibiotic resistance by this, and it became toxic over time, and which decreased the strength of the material and increased water sorption, leaded to making the material very porous. Now let us look into how the nanoparticles of chlorhexidine helped the composite in a better way. So chlorhexidine nanoparticles were added with nanoparticles of amorphous calcium phosphate, where they showed excellent mechanical, antibacterial, and remineralizing properties. Chlorhexidine was shaped into mesoporous elements and added with silica nanoparticles, which achieved the balance between the bonding strength and effective inhibition of Streptococcus mutans, biofilm growth, and increased the shelf life of these materials. And of course, lastly, the chlorhexidine, when used as nanotubes in this material, had shown that there were increased depth of cure and enhanced the mechanical as well as the biological property. Now let us go into the next aspect, that is quaternary ammonium compounds. These are also they also have a long history in the field of dentistry as in the aspect of perio lesions. They were used initially as a preservative in ophthalmic and nasal spray. They were used again in composite because they maintain the mechanical as well as the physical properties. However, the main drawback of this quaternary ammonium compound was that when you wanted to add this component into composite, it could not be added alone. It wanted some other materials to be combined with itself to stay into composite. So the other components which were used with this quaternary ammonium compound lead to toxicity. Thus, there were still some drawbacks when the plain quaternary ammonium compounds were used. However, there are many filler types of these compounds, but benzalkonium chloride is the one which is most widely used and the most accepted one. So the antibacterial action is by bacterial cell lysis, where the interaction between the positively charged ions of the material acted on the negatively charged ions of the bacterial cell membrane, and it showed a long-term antibacterial effect. Now let us see how nanotechnology helped the better action of these quaternary ammonium compounds. These quaternary ammoniums were mixed with nanoparticles of calcium chloride, and even with studies where they were added with nanoparticles amorphous calcium phosphate, and even silver nanoparticles of silver. Then even there were studies where it was added with chlorhexidine, titanium oxide, and even nanosilver. All these studies showed that when quaternary ammonium compounds were added, it reduces the metabolic activity, reduces the acid production of the biofilms, and gave enhanced remineralizing ability of the materials. However, when this compound was added into composite, the other elements which were also needed for this addition were not acceptable. First, it was mainly used in adhesive. Now, adhesive is something that is used when composite is added to a tooth. The in-between layer is called an adhesive. That is it acts like a gum. It actually helps in the attachment of composite to the tooth. So this quaternary ammonium compounds were much widely accepted when they were used in dentin bonding agents. So instead of using in composites directly, they were indirectly used in the adhesives that were needed for the composite to attach onto the tooth structure. So this is where the nanofillers of the quaternary ammonium compounds help in the better bonding of these structures and giving out a desirable antibacterial effect. Now moving on to the next one is the silver particles. Silver particles again have a long back history where they exhibited their antibacterial action by having coating over the surgical catheters, bone cements, and even dressings. Their antibacterial action was by affecting the DNA replication process, and the filler types that were used were silver zirconia phosphate or silver silica gel. And the advantages was that it maintained the mechanical as well as the physical properties, and even it enhanced the antibacterial properties. It was shown that the silver particles had its own antibacterial activity, and even it encouraged the other antibacterial activity of the elements which were joined with this in the composite. However, there still were some drawbacks if they were used plain. That is, they showed discoloration resistance, and they were even seen to show pass the blood-brain barrier. Now let us see how the nanoparticles of silver nanofillers of these silver were used. These nanoparticles were combined with nanoparticles of amorphous calcium phosphate, where it showed dual benefits of antibacterial action as well as the remineralization capability. And they were also added with quaternary ammonium compounds to inhibit the dental plaque biofilms and increase the antibacterial activity. Then so they were even again solely used as silver sodium hydrogen zirconium phosphate, similar to control. They were similar with the already available composites, and they had enhanced antibacterial efficacy. They were even used as silver phosphate, calcium phosphate, and silver nanoparticles, where they maintained the mixed phosphate particles presented higher fracture strength. That is, the material had increased strength and elastic modulus, thus where calcium phosphate particles were used. So different forms of these silver particles in the form of nanofillers enhance the mechanical, physical, as well as the biological activity of the materials. So they were even associated with acrylic resins, resin co-monomers, adhesives, intracanal medicaments, and implant coating. However, the main drawback of this silver particles was discoloration. So this was later told that 1% of silver particles when added into composite did not go ahead with any discoloration, and they were a very good outcome of this silver particle. Now let's just move on to the next aspect, that is triclosan. till now, whatever I have explained, those are the particles, those were the elements which were used in the filler part of the composite. But triclosan and the next element were used in the organic part of the composite, which is the matrix. So this is used in the liquid component, that is the base of the material. Again, triclosan has its own history where it is used in toothpaste, cosmetic products, soaps, and detergents. And its antibacterial action is upon the FEB pathway of bacterial enzymes. It interrupts the enzymatic activity of the bacteria. And triclosan is used alone. It does not have any different filler types. And again, addition of triclosan did not change the mechanical as well as the physical properties. And however, again, the triclosan had its own disadvantage, that is discoloration and sometimes resistance to this material. So now let us look into the nanotechnology aspect of this one. This triclosan, when added into monomer, causes harmful effects not at all at the level of molecular as well as the cellular levels of Streptococcus mutans. There was a reduction in the virulence of these microorganisms as well. And this triclosan methacrylate monomer reduces the bacterial adhesion and the biofilm formation. This might prevent the formation of secondary caries. And these triclosan were loaded with halosite nanotubes, which showed the improvement in physicochemical and mechanical properties. However, with all these studies, we came to know that, of course, triclosan had good antibacterial activity, but the good activity, and it did not affect the mechanical as well as the physicochemical properties of the material. But still, there is a lot of research needed where we can see how much of nanotubes or the types of nanotechnology can be incorporated with triclosan in the composite, because it is not not added in the filler component, but as it is added in the matrix component. Lastly, we'll go into the polylysine. It is also having a history, a long back history, where it is used as a food preservative, drug delivery carrier, endotoxin remover, disinfectant, emulsifying agent, and even used for bone infection. The antibacterial action is it increases the reactive oxygen species and interrupts the RNA transcription process and disrupts the bacterial cell membrane. And the action of composite was it improved the bonding of this material to the tooth structure and gave a stability of this composite. And it was even produced scientifically. And the advantages of this polylysine is that it was biodegradable, water soluble, edible, and non-toxic into humans. And it had safe levels up to 50 milligrams per kg in food. And the main advantage was it was not at all absorbed by the GI tract. Now let us look into the aspects of nanotechnology of this polylysine. Polylysine was added with nanoparticles of calcium phosphate minerals where low polymerization shrinkage was seen. It reduced the bacterial microleakage and reduced the surface roughness upon wear. And polylysine, when added with the biomimetic material, these nanocomposites showed good bonding to the tooth structure. And while polylysine was also added in smart composites, smart composites are also called as nanocomposites, 2% of polylysine was enough to improve the bonding between the tooth structure. However, fewer studies with nanotechnology have been done, but polylysine has shown that it has a good ample amount of antibacterial activity, that it can be used in composite. But again, it is used in the organic matrix, not in the filler part. So different types of structures could be incorporated in this polylysine to be incorporated in composite. However, the addition of this polylysine had a major advantage that we would not need any activator, initiator, or accelerator when polylysine was added. Thus, when we see the future aspects of this nanodentistry, there are three things that we need to keep in mind. First is that when we need to put any antibacterial agent into composite, we need to make sure that that antibacterial agent, when added into composite in the form of nanoparticles or nanotubes or nanomesopores, it had to give out the maximum antibacterial property without disrupting the basic property of the composite, that is the strength or the wear resistance or the shrinkage. And second, if the antibacterial agent has been added, other agents which could be added with the antibacterial agent have to give enhanced ability. That is, certain elements like demineralizing agents, agents which would bring about color stability and avoid the polymerization shrinkage, when added with these antibacterial agents, should have a synergistic effect on the composites. And lastly, if one component of a bacterial agent is added, if any two components of antibacterial agents are added, they should have combined effect and they should work up to their potential. So there are many aspects the nanotechnology has brought forth many improvements to visualize these materials architecture on nanoscale resolution. For example, micro leakage to nano leakage development of the resin-based composites, and nanodentistry is the art of treating the oral diseases and improving the oral health by means of nanometer level materials. The current restorative materials, such as are typically bioengineered and replace the missing volume of the tooth cavity. It is beneficial for future restorative materials to not only replace the missing volume but also be bioactive and have beneficial therapeutic actions. Such desirable properties include the antibacterial activity, inhibit the biofilm acids, and remineralizing capability to reserve the tooth decay. Nanotechnology is playing a key role in the development of these bioactive restorative materials. Thus, in conclusion, I would like to say the application of nanomaterials is the most challenging in the field of medicine and biomedical purpose. This is an area of very active research all around the globe involving a lot of research funding. It can be expected in future that the science of dental materials may change significantly with better understanding and the introduction of new biomaterials. Lastly, I would like to thank the organizing team of ISCNMB 2021 for giving me a platform to present my paper. Thank you.
Thank you very much to Dr. Aksha Shaki to this session to the allow me to ask one to Dr. Aksha. Okay, Dr. Aksha, so in
yes,
this application, how long it can stand? I mean, your fillers inside the dental restoration.
You're telling me how long do they actually stay in the material?
Yeah, correct.
Yes, sir. Sir, there have been many studies which have been carried out in this aspect. So the initial antibacterial agents, when incorporated in the composite, showed a very long antibacterial activity. That's why even though the documented cases have been up to 5 or 10 years, but we wanted to know that if there were any materials that could be incorporated in composite which had recharging ability, even by chance, if the antibacterial activity decreases over time, we wanted these materials to have the recharging ability. That means if the material is there in the mouth, if we gargle or use any oral hygiene aids with antibacterial agents, those materials had the property to incorporate those elements also to recharge themselves. So this property of recharging was also brought about by nanotechnology.
Okay, allow me to ask second question. Okay,
yes, sir.
So you are using filler or to put fillers in base material rather than a resin.
I'm sorry, sir, I cannot hear you. Can you just repeat the question, please?
So fillers distance fillers with ceramic based material in order to replace the resin component.
Hello.
Hello.
Yes, sir. Yes, sir.
Okay, my question: is it possible to replace fillers-based filler in the ceramic-based material?
Filler-based materials. Initially, the antibacterial agents were added in the filler components. That is, they wanted to coat the filler particles. Those filler matrix were divided into nanoclusters and nanomeric compounds. So they wanted to add these antibacterial agents in the filler component, whether they were nanoclusters or nanomeric compounds. So initially they had good results, but they did not give a potential antibacterial activity. That's why they changed whether we added in the filler component, let us add into the monomer component. So these are the studies where there was shift in the addition of the antibacterial agent.
Okay, thank you very much.
Yes, sir.
I pass the session to the secretary. Thank you.
Hi, Aksha. Thanks for your nice presentation. I have a question.
Yes, sir.
What is the updated application for the nanofiller? I mean, do you have any advanced application of nanofiller?
Advanced application of nanofillers is that the particle size they've tried to see different sizes of nanofillers. Right now, they are trying to see if many mixture of these nanofillers can be done. That is, initially there was 25 to 70 nanometers which were used. Nowadays, they try to go as low as possible because the lesser the amount of fillers, the more of the surface area. So nowadays they are incorporating titanium oxide with a range of almost 2 to 20 nanomeric particles. So this size have shown better properties of the composite materials.
So composite, I mean, which composite you can use?
In composite, it depends on the type of, actually, sir, when you see the places where they can use, if you want aesthetic, for example, composite, if you want to apply on the anterior aspect, that's the front part of your mouth, so there it is something, their occlusal load will not be so much, but there will be aesthetic of main concern. The type of composite can be based where the composite which will show you good optical properties. So in that area, you'll go ahead with composite with good optical properties. And if composite, if you want to apply on the back region, that is posterior region, where aesthetic is not a major concern, but occlusion loading is main important. So you will choose composites where they have the ability to take up the occlusion load.
Thank you so much. Yeah. Thank you.
Okay, thank you, Dr. Arshia.
Thank you, Dr. Arshia Shakir, for the interesting presentation, and Professor Dr. Mustafa for chairing this session. Before we move on to the next presentation, is there any question from the audience? If not, Dr. Arshia?
Yes, sir.
Do you want to be the next chairperson for the next presentation?
Sure, sir. I don't mind.
All right, and then we can move on to the next presenter, Dr. L. Anandaraj from the Sacred Heart College, Autonomous, India, to present about synthesis, growth, and characterization of benzophenone added sodium acid phthalate crystal, a potential material for nonlinear optical application. I would like to also invite Dr. Arshia Shakir to chair this session. Dr. Anandaraj, are you there?
Dr. Anandaraj, please unmute your mic. Are you available, sir, to start your talk? So please, Dr. Anandaraj.
Yeah, good morning. I am here.
Yeah, we can hear. Sir, do you can switch your camera? Switch on your camera.
Yes, sir. Okay.
Yeah. Okay, Dr. Sundar, suppose it's Dr. Anandaraj slot. Maybe it's I don't know what's happening. So if you can, if you possible to start your presentation, so we jump to the EULA, sir. So maybe Dr. Arshia can chair the session for Dr. Sundar Singh.
Yes, sir. I am ready.
Very good morning to Dr. Sundar Singh. He's from the Department of Physics, Bareilly College, UP. I welcome you, sir, for your invited lecture. And he's going to give a lecture on photo anode optimization approaches for enhanced efficiency on quantum dot sensitized solar cells. Sir, I welcome you, sir, and please, sir.
Thank you, Dr. Arshia. Hello. Hello.
Yes, sir.
Yeah, am I audible, madam?
Yes, sir. You're even audible. I can see your slide also.
Okay, thank you. Thank you, madam, for giving me this opportunity to interact and present before you people. And I would also like to thank the organizers of this international summits and conference on material science, nanotechnology, and biomanufacturing, ISCMNB 2021, especially to Dr. Tinakaran and Professor Paul. The topic that I have chosen to present today is the photoanode optimization approaches for enhanced efficiency quantum dot sensitized solar cells. I have divided my talk into these components. First, I will talk about solar cells. Then I will give some introduction of quantum dots, and then quantum dots based solar cells or quantum dot sensitized solar cells, and then photoanode optimization approaches which are being used for enhancing the photovoltaic performance of these quantum dot sensitized solar cells, and finally I will come to the conclusion. So first, as we all know, solar cells are devices which can convert solar energy into electrical energy by the use of photovoltaic effect. And in this device, there must be some material to absorb light, and then the process of charge separation must take place, that is in terms of electrons and holes, and finally there should be the transport of charge between the electrodes for the completion of this conversion process. Here are some parameters which are important for the judgment of photovoltaic performance of a device. These are basically open circuit voltage, short circuit current, fill factor, very important parameter, and then the power conversion efficiency. This Shockley user limit for single PN junction device based upon the thermodynamic balance was around 33.7%, and this corresponds to a band gap of around 1.34 electron volt. Now silicon, as we all know, has an indirect band gap of 1.1 electron volt. So initially it was taken as a material for the development of solar cells. So in terms of first generation solar cells, these devices were based on single crystalline silicon solar cells. So large single crystals of silicon were developed, and this silicon, because of indirect band gap, in this process a phonon is also involved. So this gives rise to low absorption coefficient, and at the same time requirement of fairly thick single crystals. So the fabrication process becomes quite high, but the efficiency is also good. Around 26% maximum efficiency can be achieved with the help of these single crystalline based silicon solar cells. Then another solar cell based upon polycrystalline silicon solar cells, which have maximum efficiency around 22%, but the problem is that they are less efficient as compared to the single crystalline silicon solar cells. But the advantage is that their cost is low because the silicon wafers are not needed for their fabrication. So the process becomes less costly. Then in terms of the second generation thin film solar cells, based upon the materials cadmium telluride, cadmium, indium, gallium selenide, and amorphous silicon. This amorphous silicon based solar cells are basically very important. This amorphous silicon has direct band gap in contrast to the single crystalline silicon, which has indirect band gap. Here, the direct band gap provides it a higher absorption coefficient, but the problem is that because of the lower mobility of charge carrier in this material, these devices are less efficient as compared to crystalline silicon based. Now, finally, the third generation, which is the current generation of solar cells, it includes dye-sensitized solar cells, perovskite solar cells, quantum dot sensitized solar cells, and organic solar cells. Here, the concepts like multiple exciton generation, which are the advanced photovoltaic concepts, may be used, which give them lower cost as well as very high efficiency. The high efficiency there is a possibility of crossing the Sokolov user limit also. Now, in these dye-sensitized solar cells, organic or ruthenium dyes are used for the sensitization purpose of, so that the light harvesting is increased. These perovskite solar cells are quite efficient and they promise efficiency around 25%. Perovskites are basically the materials which have a crystal structure of calcium titanate, CaTiO3, where and these are basically cheaper than gallium arsenide or gallium phosphide, like third, fifth semiconductors. Then the main category here which I want to discuss is the quantum dot sensitized solar cells, which I will cover in major part of my talk, and then graphene solar cells also. Graphene is a two-dimensional sheet-like material which has very excellent properties. It is very flexible, optically transparent, and it is ideal for thin film solar cells. And it has a very high electron mobility, so it can be used as a carrier transport material, and stability is also very high. Now, quantum dots. These are basically nanoparticles of semiconducting materials having diameters in the range 2 to 10 nanometers, and their size is less than the exciton Bohr radius of the corresponding bulk material, and the size is small. Quantum confinement phenomena takes place, and because of that the energy levels are discrete, and since they show discrete energy levels, so they are sometimes known as artificial atoms because of the presence of these discrete energy levels. In terms of number of atoms they contain or the dimensions, they lie between the molecular forms of matter and bulk forms of matter. They can be fabricated by using the semiconducting materials like lead sulfide, lead selenide, cadmium sulfide, cadmium selenide. These cadmium selenide and cadmium telluride are very important for the solar cell purposes. Also, these quantum dots show very sharp density of states which provide them good transport and optical properties. These are basically inorganic in nature, and most importantly, they have size dependent emission colors, which I have shown here. Here, the excitation light is blue. That means the same wavelength light is made incident on all these different size quantum dots. 2 nanometer, 2.5 nanometer, 3 nanometer, up to 6 nanometer. And we can see that the color of emitted light is different. It is varying from, according to the size of the quantum dot. Now, come to the quantum dot sensitized solar cells. The purpose of using quantum dots in these solar cells is the to harvest more light. Now these quantum dots, because of their excellent properties, extend the absorption vision. Not only visible light is harvested by these, but they, because of their band gap engineering facility, they make available infrared energy also, so that broader absorption, they have broader absorption spectrum, more solar energy can be used for the conversion into electrical energy. And for this purpose, direct band gap quantum dots having narrow and direct band gap quantum dots are preferred because of high optical absorption coefficients. Now, if we talk about the structure of quantum dot sensitized solar cells, then there are four important components of these quantum dot sensitized solar cells. First is the photoanode, which is in most cases a TiO2 film or some other material, or in different types of structures. And for more harvesting of light, sensitizer is used, and here quantum dots are used for a sensitizing material, like a sensitizing material. Then there must be some electrolyte, normally iodide or polysulfide electrolytes are used, and then a counter electrode or photocathode, which is mostly platinum or Cu2s. Now, why we use quantum dots for sensitization purpose? This is because of their outstanding properties. They have the facility of tunable band gap. That means their band gap can be changed by changing their composition as well as their size. If size changes, then their band gap changes, and if their composition is changed, then also their band gap can change. Also, there is a facility of solution processing of quantum dots, and they also show high stability against light as compared to the dye molecules, and most importantly, the possibility of multiple exciton generation. Upon absorption of single photon, there is a possibility of creation of more than one electron hole pair. So this possibility of multiple exciton generation provides the facility of crossing the Shockley-Cuser limit for these devices in terms of their power conversion efficiencies. Here I have shown the different components of dye sensitized solar cells or quantum dot sensitized solar cells. Photoanode, which is in most cases TiO2 or ZNO material. TiO2 is normally used because of its properties, because it is non-toxic, less expensive, and it is easily available also. Sensitizers के लिए for sensitizers we use quantum dots in case of QDSSCs, and dye molecules for DSSCs. Then electrolyte, the function of electrolyte is to allow fast diffusion of charge carriers. It also helps in the regeneration of sensitizer, and it creates effective contact between the two electrodes of the device. Now, solid state electrolytes are seen as better performing electrolytes as compared to the liquid electrolytes, because liquid electrolytes have some problems. Now, counter electrode. This counter electrode is basically platinum coated FTO or Cu2s coated FTO. Thin layer of platinum or Cu2s coating on FTO, fluorine doped tin oxide. The purpose of using this is to catalyze the reduction of liquid electrolyte and for the efficient charge collection. Here are some of the advantages of these devices and disadvantages. So advantages, if I talk about advantages, the simple fabrication techniques of these devices and the high absorption coefficient associated with the sensitizing materials. And these have high stability. Secondly, the power conversion is also available at low costs as compared to silicon-based devices. Now, if I talk about disadvantages, then the presence of surface defects because of the high surface to volume ratio of these materials. These surface defects can act as temporary traps and which can lead to increased charge recombination. Now, increased charge recombination deteriorates the photovoltaic performance of a device. So, to increase the efficiency of device, there should be mechanisms for discouraging the charge carrier recombination. Now, one approach to this to reduce recombination is the passivation of the quantum dots, and this structure, core cell structure, may be used, but there are some disadvantages also associated with this structure. Now, why we need optimization of different components? We have seen that theoretical maximum limit for quantum dot sensitized solar cells may be 44%. So their theoretical efficiency may reach up to 44%. Whereas till now, the highly efficient quantum dot sensitized solar cells reported so far is around 14%. So there is a large gap between the theoretical possible efficiency and the practically available quantum dot sensitized solar cell devices. So this means that the optimization of different components or materials used in the fabrication of quantum dot sensitized solar cells is to be done still there. Now, these are the 4 components which must be optimized for enhancing the efficiency or for improving the performance of these devices. Now, first component is the photoanode. Now, this photoanode, its material may be optimized as well as its structure or architecture may be optimized. The purpose is to that there should be higher loading of sensitizing material, that is the quantum dots. So we have to choose materials or optimize materials so that they can lead to higher loading of quantum dots, so that there is increased absorption and enhanced efficiency of the devices. Now, for this, photoanodes may be prepared from different kinds of nanostructures, may be used nanotubes, nanorods, and these may be fabricated with the help of metal doped films also. Then the second component, that is the sensitizers. In this case, quantum dots are the sensitizing materials. The quantum dots must also be synthesized, different quantum dots, and the purpose is to broaden the absorption spectrum, to broaden the light harvesting range. So if we go beyond the visible light range, we can if we are able to harvest the infrared light also, then the efficiency of these devices can be increased. Secondly is to dope these quantum dots with transition metal ions, which will also lead to enhanced light harvesting. Then the third component, that is the electrolytes. These electrolytes may be quasi-solid, solid, or liquid. So different kinds of electrolytes may be used for this efficiency enhancement purpose. Now, counter electrodes. The counter electrodes may be developed with enhanced electrocatalytic activity so that they can lead to higher efficiency for the devices. The first, here I have discussed about nanostructured modification, surface modification of nanostructures. So MOS, metal oxide semiconductor, which is normally used for the photo anode, TiO2 or ZNO. It has large specific surface area and also the high scattering effect. The large specific area helps in the higher loading of sensitizing material, whereas strong scattering effect helps in sufficient absorption of photons. But at the same time, the disadvantages associated with this structure are this large surface area also leads to increased recombination, and the presence of surface defects may retard the effective charge injection and also to the charge transport. So the surface modification may be applied for MOS as well as for quantum dots, which will lead to lower recombination and improved transport of carriers, ultimately resulting into increased efficiency for the device. So here, without modification, the absorbance is lower, and with modification, the absorbance has increased. Then we can apply this mixed metal oxide technique also, graphene doped mixed metal oxides. Here zinc and titanium are the metals, and graphene is doped in this mixed metal oxide to enhance the efficiency. These graphene sheets were produced by supercritical CO2 exfoliation of graphite. Now, graphene is basically a 2D material and an allotropic form of carbon, which has very important properties as for the purpose of these photovoltaic devices. And then zinc titanium mixed metal oxide, these were combined and for developing the hybrid materials for photo anode, graphene doped mixed metal oxide hybrid materials for photo anode. Now, the presence of graphene in this material was confirmed by the help of these characterization techniques, Raman spectroscopy, X-ray diffraction, and energy dispersive X-ray spectroscopy, and the different concentration effects of graphene on the performance of CDS sensitized quantum dot sensitized solar cells was studied with the help of electrochemical impedance spectroscopy technique. Now the graphene was added to this mixed metal oxide to enhance the adsorption properties of quantum dots, and it also resulted into lower internal resistance, ultimately leading to some enhanced photovoltaic performance of the device. Although not very high efficiency could be obtained with this approach. Then here is the approach using the one-dimensional connected nanoparticles for fabricating photo anode. Now, this one-dimensional connected nanoparticle based photo anode is based upon the advantages of TiO2 nanoparticles, which have high specific surface area, and one-dimensional nanostructures. One-dimensional nanostructures are useful as fast transport channels. So these nanostructures like nanowires and nanotubes. So these combine, this photo anode combines the advantages of these two nanoparticles as well as one-dimensional nanostructures. And this solvothermal method was used for synthesis of these one-dimensional connected TiO2 nanoparticles and for developing the photo anode for this CDSE sensitized quantum dots sensitized solar cells. Now, an efficiency of 5.45% could be obtained with slightly higher open circuit voltage and relatively higher short circuit current density. These one-dimensional connected nanoparticles has large pores, and because of these large pores, they have a relatively large specific surface area, and which leads to higher loading of quantum dots for efficient harvesting of light. This also results into reduced recombination as well as efficient electron transport. The efficiency increased because of the enhanced harvesting of light and good charge collection efficiency. Here is the basic structure, how the photo anode fabrication process took place. So first of all, CDSE sensitized Ti2 film were developed. Then for these were coated with ZNS zinc sulfide, and then another layer of SiO2 over this coating was applied, and finally then the ZNS SiO2 passivated TiO2 film photo anode was developed after the sintering process. Here is the tri-layer photoanode structure, which makes use of TiO2 nanofiber layer sandwiched between two layers of P25 TiO2 nanoparticles. So this tri-layer nanostructure has improved light harvesting because of the multiple scattering of light in this structure, and efficient electron transport due to the presence of nanofiber layer. And this also resulted into lower recombination values. So because of these features, performance of this tri-layer photoanode was better as compared to single layer TiO2 nanoparticle based photoanode, and this performance increase, there is a possibility of further improvement by using these processes. Now the photovoltaic performance for this device is here. Short circuit current density around 13 milliampere per centimeter square, but the this open circuit voltage is quite high. So this device, this structure may be used for enhancing the efficiency of quantum dot sensitized solar cells. Here is another structure which makes use of double photoanode. So two photoanodes. This is the first photoanode and this is the another photoanode. In between them, this is the Cu2s mass counter electrode or photocathode. So double photoanode is here, and here is the mechanism for the concentrating photovoltaics, for using concentrating photovoltaic concept. So by using this concept and a double photoanode design, the efficiency was very high. The champion cell efficiency of champion cell returned around 8.28% with exceptionally high short circuit current 32.247 milliampere per centimeter square and quite high open circuit voltage also. Now this improved performance is due to the photothermal effect because of the use of this CPV concept, which accelerated the conversion of polysulfide species, and secondly the CPV concept also leads to more light capture also, so which resulted into increased short circuit current. Here I have compared the tri-layer photoanode structure with this double photoanode design. So we can see that there is a great difference between the short circuit current densities. This double photoanode design has a very high current density, but here in terms of open circuit voltage we can see that not very great difference between the two structures, but again there is a great difference between the efficiency values of these two devices. Now Cu2O TiO2 nanocomposite photoanode, another approach which makes use of Cu2O nanoparticles for the doping of TiO2 photoanode, and the solar cells were CDS or CDSE sensitized. Both were tested. The counter electrode was of copper sulfide CUS, and CUS counter electrode, and polysulfide or sulfide was used as electrolyte. Now in this case also lower recombination and fast electron transfer resulted into the increased or enhanced performance of the device. If we see that TiO2 photoanode without CO2O doping is having these parameters, photovoltaic parameters, whereas if we make this nanocomposite CO2O TiO2 nanocomposite, then the photoanode based upon this nanocomposite have relatively improved performance. Another approach involves the coating of these TiO2 nanoparticles, coated ZNO nanorod based arrows photoanode. Here ZNO is having high electron mobility, and it can be fabricated with the help of different strategies like atomic layer deposition, hydrothermal, etc. Possible structures may be one-dimensional, two-dimensional, three-dimensional, but the most common structure being used here is the one-dimensional nanostructures like nanowires, nanotubes, nanorods, because of the facility of fast transport of electrons and the less recombination of lower recombination of charges. This composite nanostructure, because of enhanced surface area of nanoparticles, improved electron transport by nanorods, and lower recombination centers, resulted into increased performance. Here, reduced recombination, longer electron lifetime, and power conversion efficiency was also quite high, relatively high, 4.8%. Whereas without passivation, without TiO2 passivation, these Giordano nanorod arrays resulted into an efficiency of 2.7%. Here is another structure in which copper indium selenide quantum dots were used for the sensitizing purpose of TiO2 photoanode, and several layers of CDS coating were developed by using the Cellar technique, and ZNS was used as a last passivation layer. So this is just a schematic, not the actual one, and this structure resulted into higher surface coverage of TiO2 by the sensitizing material, that is the quantum dots, and this also resulted into lesser recombination of photo-generated electrons and holes, which leads to a longer electron lifetime and gave rise to high open circuit voltage around this 0.6 something, 0.56. Here I have compared some structures for their photovoltaic performance, and we can see that this structure, which makes use of the CPV concept and the double photoanode, has the highest short circuit current density, and it has also a very high open circuit voltage. The fill factor is not very high, it is relatively low, so there is a possibility of increasing this factor for even improved performance. Efficiency, in terms of efficiency, all these devices, I compare all these devices, then this structure has the highest efficiency. Now coming to the conclusion, quantum dots have excellent optoelectronic properties, like their band gap can be tuned to different portions of visible light or infrared light or other, because of the band gap engineering facility, by changing their size and composition. And these materials have wide absorption spectrum, good stability against light, and the facility of solution processable techniques. Then all these things lead to lower production costs also, and the possibility of multiple exciton generation, which is very promising for providing these devices, quantum dots based devices, to cross the theoretical power conversion limit. Optimization of photoanode structure and materials is very crucial for obtaining high power conversion efficiencies from these devices. And the double photoanode structure for the devices that I have included in this talk has the high PC power conversion efficiency. Even higher power conversion efficiencies can be obtained if counter electrodes optimization is also utilized. As far as my knowledge is concerned, or I know, I just reported PCE is around 14% for quantum dot sensitized solar cells, which makes use of carbon nanotubes, graphene hydrogel, and COS composite counter electrodes. And in this structure, TiO2 photoanode was sensitized with ZnCu indium selenide quantum dots. So this is all about from my side. Thank you.
All right, thank you, Dr. Sundar Singh, for the interesting presentation, and Dr. Aisha Shakir for chairing this session. Is there any questions from the audience?
Dr. Sundar.
No.
Sir.
Very interesting topic, sir, about the solar. Sir, I just want to, hello? Can you hear me, sir?
Yeah, I'm hearing you.
Yeah. Just I want to few curiosity about the. You mentioned about the what. You go to the conclusion, sir. Can go to the slide conclusion.
Here.
Conclusion slide. The last slide.
Last slide. Oh, yeah.
Yes. You mentioned about the absorption. What absorption spectrum is it?
Yeah.
How it's possible, sir? Can you explain in brief what this?
Actually, the band gap of quantum dots can be changed by changing their composition. So, without changing the techniques, without changing the manufacturing techniques, or without changing the material, these quantum dots, by changing their size or by changing their composition, we can change their band gap. And this change in band gap provides us facility of tuning different portions of solar spectrum. So we can broaden the absorption spectrum of quantum dots by changing their band.
Thank you, sir. Thanks
for okay, thank you very much, sir.
Yeah, Dr. Sundar Singh, I have one question. Is that, I mean, how you gradually increase the efficiency of your solar system?
Well, I think there are two mechanisms. Either we optimize the material of the components, or we change the structure. We try different structures. So here, if I talk about photoanodes, so we can try different materials for the fabrication of photoanodes. So different materials, by testing different materials, we can see that there is, we will find or we will optimize some material which gives us higher efficiency, or we can use different kinds of nanostructures, because to increase efficiency, what we have to do is we have to ensure lower recombination and to ensure higher harvesting of light, right? So we have to find out some mechanism by changing materials or by changing nanostructures, so that we achieve lesser recombination and higher absorption of light, so that we can increase the efficiency of the device.
Dr. Sundar Singh, this is Arshia. Even I have a few questions, sir. Though this quantum dots have been very exclusively discussed right now, but I want to know what made you actually use this, or what is the main purpose for you to use in the solar cells?
The main use of these quantum dots is basically for the sensitization purpose of the photoanode. Now the purpose is that we want to absorb more and more light.
Okay.
Broader spectrum of light, I mean to say from ultraviolet to infrared, we want to absorb all portions of light. So to that absorption, to make more absorption of light, we make use of these quantum dots for the sensitizing of photoanode.
Okay, sir. And it is basically size dependent also. And how does it differ based on the size, sir? The emission of these dots, sir?
Size basically decides their band gap, and band gap means the wavelength. If we change the band gap, so absorption and emission wavelength will also change.
Which is the desirable wavelength that you would like to actually incorporate, sir?
Actually, most of the quantum dots, if the band gap is higher, then the wavelength will be lower. So these narrow band gap semiconductors are mainly used for harvesting of the infrared portions of light.
Okay, sir. This is a little bit out of the way, but do you know any other roles of these quantum dots in other fields where they are used, sir, other than solar cells?
These quantum dots may be used for diagnostic purposes.
Okay.
We all know that MRI contrast, these quantum dots may be used as MRI contrast agents also, and quantum dots are also used for I think as
let me add to that point, sir. Nowadays, as we all know, this is a COVID situation going almost all over the world. So, quantum dots have also played a major role in our field, where we have there are many studies they are trying to prove where quantum dots have been used as biosensors and as even as antiviral agents for the stoppage of viral infection. So there are certain studies going on where quantum dots have played a major role in stopping the COVID-19 vaccine. So thank you very much for your presentation, sir.
Okay, my pleasure, my pleasure. Thank you, organizers also for giving me this opportunity.
Okay, is there any other questions from the audience? If no, Dr. Sundar Singh. Dr. Sundar Singh, can you hear me?
Yeah.
Would you like to be the next chairperson for the next presentation?
Sure, sir.
All right. We then move on to the next presenter, Dr. L. Anandaraj from Sacred Heart College, Autonomous of India, to present about synthesis, growth, and characterization of benzophenone added sodium and acid phthalate crystal, a potential material for nonlinear optical applications. Dr. L. Anandaraj, are you there?
Yes, sir. Yes, sir. Shall I start?
I would also like.
Okay.
Right. I would like to invite Dr. Sundar Singh to chair this session.
Okay, thank you for giving me this opportunity to conduct this session. I welcome Dr. L. Anandaraj from PG and Research Department of Physics, Sacred Hearts College, Tamil Nadu. And he will be, sorry, topic I missed. Just a minute. Yeah, sorry. Dr. L. Anandaraj belongs to PG and Research Department of Physics, Sacred Hearts College, which is an autonomous college in Tamil Nadu, India. And he will be talking about synthesis, growth, and characterization of benzophenone added sodium acid phthalate crystal, a potential material for non-linear optical applications. So I welcome Dr. L. Anandaraj, and you may proceed now. Dr. L. Anandaraj.
Yes, thank you, sir. Thank you. Sir, is it visible?
Yes, you are visible. Your slides are visible.
Okay. Thank you, sir. A very good morning to one and all present here. My topic is synthesis, growth, and characterization of benzophenone added sodium acid phthalate crystal, a potential material for non-linear optical applications. Okay, this is Anandaraj. from assistant professor from Sacred College, Triputtur, Tamil Nadu. The outline of this topic is introduction, method adopted for crystal growth, synthesis, characterization studies, conclusion, and references. First of all, the introduction about the topic, about the material. So why I chose this material? Here focuses much on the search for highly efficient second order nonlinear optical material due to their potential applications in various fields. Doping of external impurities plays a crucial role in turning the properties of the host crystal. Semi-organic NLO crystals have a wide range of applications like the high transparency range. In this present work, we report the repercussion of a benzophenone in sodium acid thalate single crystal for SHG second harmonic generation applications. Already, many papers are reported using sodium acid thalate. They got very good result for NLO application. So that I chose sodium acid thalate and also the benzophenone. So here I am using the method adapted for crystal growth, slow evaporation method. Yeah, everybody know about the slow evaporation method. So this is very easiest method and also it is very low cost. So there are many methods used to synthesize crystals. So we know that one of these easiest method is the slow evaporation method. Here the compound can be dissolved with a single solvent or a mixture of two solvents of left for slow evaporation. Here the advantages of this method is that easy and its disadvantages is that needs to lot of material, which is not so good for air sensitive compounds. So next one is the synthesis. Here the sodium acid.
Sorry for the interruption. Can you please make your slideshow mode because it is not visible properly. Slideshow mode.
Oh.
Yeah. Go for slideshow mode.
Yes.
Please go at the top button. Yes. There. Click. Not that. Not this one. Just yes. This one. Slideshow from current slide. Now you go the bar from current slide. Yes. Not this one. Yes. You can. Yes. Custom slide.
Okay. Is it okay, sir?
Click there. From current slide, go just from current slide, not custom.
Oh.
From current slide. Yes, this one, yes. Click there. Click there.
Yes. Sir, now is it okay?
No. Go for current slide. Just click on current slide.
Yes, sir. Already I clicked only current slide from current slide.
Okay, not visible. Okay. Go ahead, please.
You can choose third option from the bottom taskbar also. This one. Near 70%.
Okay, please proceed.
Okay, you may proceed now. Okay. So here the sodium acid thalate was synthesized by sodium hydroxide and phthalic acid in equimolar ratio 1:1, and it is dissolved in a deionized water. So the solution was magnetically stirred for 1 hour. After that, the dopant benzophenone was dissolved in 35 ml of deionized water and stirred for 1 hour. And finally, both solution was mixed together and continuously stirred for 3 hours. After stirring process, sample solution is filtered using the Whatman filter paper, and it is kept at the room temperature for slow evaporation method. And the nucleation starts at after 20 days. Finally, got a good transparent crystal was grown up with the dimensions 11 into 6 into 2 millimeter cube of the benzoquinone doped SAPP sodium acid thalate benzoquinone crystal were prepared. So this is the ground crystal SAPP, that is a sodium acid thalate benzoquinone crystal. It's one of the bulk crystals and a good transparent crystal. So next one, here I analyzed various method. The first one is a single crystal X-ray diffraction method. The single crystal X-ray diffraction studies are carried out to find lattice parameters as compared to the powder XRD studies. The single crystal XRD results declares that the benzoquinone doped with the sodium acid thalate crystal belongs to the monoclonic system. The unit cell dimensions and the X-ray intensity data of sodium acid thalate benzoquinone were found using Bruker D8 venture sodium single crystal XRD equipped with the MOKR for radiations. The wavelength of lambda is equal to 0.71073 angstrom with the space group B2CB. So these are the lattice parameters and the lattice parameters of a SAPP crystal. So next one is the powder XRD. The powder X-ray diffraction pattern that confirms that the crystalline nature of the ground crystal. The powder X-ray diffraction analysis of SAPP was recorded by using powder X-ray diffraction diffractometer with a CU K alpha 1 radiation. The wavelength of the powder XRD is lambda is equal to 1.54060 meter. From the spectrum, it is observed that the peaks are turned up into the between 10 to 60 degrees. The sharp and prominent peaks at 19.06 degree is assigned to the 001 crystal plane of the SAPP. So this is the spectrum of powder X-ray diffraction. So next one is FTIR analysis. It is used for effective tool to identify and confirm the compound by analyzing the functional group present within the spectrum. The molecular interaction between the reagent can be well explained by examining different modes of vibrations. Fourier transform infrared analysis was carried out between 400 to 4000 centimeter meter inverse wavelength by using KBR pellet technique. So this is the spectrum of FTIR SAPP crystal. So here peaks the wavelength 350.10 centimeter inverse is, it tells us OHO tone of the water molecules 2854.21 centimeter inverse to 2454.23 cm centimeter centi per meter. CH2 strengthening vibrations 1598.42 centimeter inverse and 1626.01 centimeter inverse C double bond O stretching of the COO group 1571.15 centimeter inverse aromatic ring structure of the SAPP crystal 1626.01 centimeter inverse NH bonding vibration 1598.42 centimeter inverse and 1571.15 centimeter inverse, that is skeletal vibrations of the aromatic ring of a benzoquinone. So next one is 1297.06 centimeter inverse aromatic amine stretching. These are the observation from FTIR. So next, UV visible NIR spectral analysis. The ground crystal of benzoquinone doped sodium acid thalate dissolved in a distilled water was subjected to spectral analysis. The optical absorption studies of the sample have been carried out in wavelength range between 200 to 11,000 nanometer. The lower cutoff wavelength of SAPP was observed to be 277 nanometer. The spectrum indicates that the crystal to be used as the promising aspirant of a higher order of a nonlinear optical generation and terahertz applications. So this is the spectrum of a transmitter and absorptions of a SAP-B crystal. So transmitters, it is more or less 95 and something. So and also the cutoff wavelength is 277 nanometer transmitters and absorption spectrum. The cutoff wavelength is 277 nanometer. This is the spectrum of observation and transmittance of the crystal. So next one is band gap to calculate to find the band gap of the crystal. So using that formula, the band gap of the SAPP crystal estimated by extrapolation of the linear part of the graph is a 4 electron volt. The property of electronic optical band gap energy can be well exploited in the field of terahertz generation and electro-optical device applications. So this is the tau plots. So band gap of the crystal is a 4 electron volt. This is the spectrum of a band gap. So next one is a fluorescence study. Fluorescence study is the prominent tool to determine the physical properties of the material at the molecular level, including salinity and purity. The fluorescence spectrum was interpreted for a SAPP crystal using variant carry eclipse fluorescence spectrometer at a room temperature. The fluorescence emission spectrum was recorded in the range of 500 to 850 nanometer. The SAPP, that is a sodium acid phthalate with a benzobenone crystal, showed a strong yellow emission peak at 574 nanometer and the red emission at 631 nanometer are identified. Here I observed the very strong peak in a yellow region and the small peak in a red region. Hence, this semi-organic molecule with the promising fluorescence emission can be exploited in the NLO applications. This is the spectrum of fluorescence. Here I am taking the x-axis is wavelength and the y-axis is the intensity. The high peak values of 574. It is a nanometer. It is a near of a yellow region, and also here we are getting the small peak, that is a 631.28. It is a red region. So next, second harmonic generation. The nonlinear optical mainly I focus only second harmonic generation of the my crystal. The nonlinear optical activity of the ground crystal is investigated through the Cos-Perry powder technique by performing the SHG test. The crystals are good ground to powder packed in a capillary tube and were exposed to the continuous band. A Q switch ND laser of fundamental wavelength 1064 nanometer, delivering 10 nanoseconds laser pulses. Following a repetition rate of 10 hertz was used. The second harmonic generation behavior in this crystal was confirmed from the emission of intense green radiation. That is, the wavelength is lambda is equal to 532 nanometer by the sample. The determined second harmonic generation efficiency of a SAPP of crystal as a 2 times superior to KDP crystal. So it is a very strong information about the second harmonic generation compared to KDP crystal. It has a 2 times greater than KDP, the second harmonic generation. So next, finally, I conclude using this crystal. Optically good quality single crystal of a benzobenone doped sodium acid phthalate crystals has been grown by slow evaporation technique. So single crystal XRD shows the structure of the crystal. Powder XRD confirms the good crystalline nature of the crystal, and the FTIR analysis confirms the bond and functional group present. UV visible spectral analysis confirms the good transparency. The small width band gap confirms the defect of free crystal. Fluorescence studies confirms the emission of yellow and red light. And finally, the second harmonic generation confirms the NLO property. These are the information about my crystal. Thank you.
Thank you, Anandaraj, for this nice presentation. And now the talk is open for discussion. Audience, if there are any queries, you may ask, please. Is there any query? Oh, yeah. Dr. Anandaraj?
Yes, sir.
I have a small query.
Yes, sir.
Yeah. You have synthesized SAPB crystals
Yes.
for non-linear optical applications. So what kind of non-linear optical applications you are trying for these SAPB crystals?
Optoelectronic devices.
Optoelectronic devices.
Yes.
So is there any temperature limitation for their synthesis?
No, sir. It has only the room temperature.
Room temperature. So synthesis can occur at room temperature also.
Yeah. Yes.
Some other limitations are also for their synthesis. I mean pressure or some other kind of.
Yes, sir. Yes, sir. Mainly, it is a very easy and low cost, but it has a lot of limitations, disadvantages also.
Okay.
We cannot measure the absolute temperature. Sometimes it may be increase or decrease.
Okay. Okay. All right. So, audience.
Hello, Dr. Anandaraj.
Yes, sir.
Very nice presentation, sir.
Thank you, sir.
All the best, sir. Thank you so much.
Thank you.
Join this conference.
Okay. Thank you, sir. Thank you.
So, if there is no other query, then let us thank the speaker. Thank you, Dr. Anandaraj, for this nice presentation.
Thank you, sir.
Okay, thank you. Thank you, Dr. L. Anandaraj, for the interesting presentation, and Dr. Sundar Singh for chairing this session.
Thank you, sir.
All right, thank you. Before we move on to the next presenter, Dr. Anandaraj.
Yes, sir.
Would you like to be the next chairperson for the next presentation?
Sorry, sir, I can't hear.
Would you like to be the next chairperson for the next presentation? Hello, doctor. Can you hear me?
Yes, sir.
Would you like to be the next chairperson?
Yes, sir. Yes, sir. Sure, sir.
All right. Wonderful. All right. We move on to the next presenter, Dr. P. Lakshmi Praveen from Veer Surendra Sai University of Technology, India, to present about probable phase, solvent-induced spectral bands, and photostability of liquid crystal, theoretical models and analysis. I would also like to invite Dr. Anandaraj to chair this session. Thank you.
Yeah, good morning to all. Yeah. So I'm Dr. P.L. Praveen from Virsudan University of Technology, Odisha, India. So first of all, I thank all the organizers, chairman, convener, Professor Paul, for giving me this excellent opportunity to share my views on some of my research findings. So here is the title of my talk: probable phase and solvent-induced spectral bands. Basically, talking about photostability of several liquid crystal molecules. And here is the outline of my presentation. So brief discovery as well as some basic building blocks of liquid crystals, and what do we do and what is the working strategy we follow, and for identification of probable phase. And here I am considering cyanobiphenyl based liquid crystal molecules, and why we are focusing on UV visible and what are the different challenges. And then I will be speaking about naphthalene based liquid crystal systems, which are excellent candidates for side chain liquid crystal polymers. And then I will go with the significance of my work as well as conclusion. So first of all, the liquid crystal phase, it is a mesophase between a pure crystal and pure isotropic melt that possesses the properties of both the states. So way back, it is found out, discovered around 1857 when the cholesterol plants were studied. So here are the basic building blocks. So two aromatic rings are there. So usually structure is represented with the two aromatic rings, but nowadays is more than two also. 2, 3, 4, 5 like this goes on. So A and B are aromatic rings, and this is a side group, linking group, and terminal group. So by varying all these possible with a number of possible combinations, we can design as well as synthesize many liquid crystal molecules. This is a huge classification of liquid crystals. So the uh, basic and more important one is thermotropic as well as allotropic. So I'll be focusing on thermotropic liquid crystals. Under that, we have pneumatic systems, magnetic system, and cholesteric system. And what's so attractive about liquid crystals usually? All the crystals are characterized by their optical properties, and all the liquids are characterized by their fluid properties. And this liquid crystal, it will have both optical anisotropy as well as these molecules can be rearranged easily by applying a very short electric field. Therefore, due to the combination of properties of both crystals and liquids, so we can exploit large electro-optical effects with only small applied voltages. So what do we do actually? We are studying different kinds of molecular interactions to simulate the materials and finally to explore the material properties. So number of non-bonded interactions we are considering. So there are basically three different types. The stacking mode interaction, in-plane mode interaction, and then terminal mode interaction. So in some of the cases, the terminal mode interactions are not so significant. So mostly the stacking and in-plane mode interactions we will be carrying out, but the third mode interaction also being taken into consideration for a better picture. So this is my working strategy. So first of all, we used to find out the actual molecular geometry from the crystallographic profile. So usually crystallographic profile that may contain some errors in some cases. So we will be removing those minute errors with and then finding out the actual molecular geometry. Then estimation of the atomic charge and atomic dipole moment distributions. Then computation of interaction energy for various configurations. Then these interaction energies are taken as input to calculate the configurational probabilities as well as thermodynamic parameters like configurational entropy and free energy. Then these parameters are correlated with the different kinds of mesogenic property, and the UV visible spectra also is taken into consideration for understanding for different kinds of applications. And this is my simple formula and as well as computational details. The pair interaction energies are taken into consideration, which is having four different components: electrostatic energy, polarization energy, dispersion energy, and repulsive energy. And once again, this electrostatic energy, this is being expanded as a monopole term, monopole dipole term. So that is why this is known as a multipole expansion method. So both together, this is a multi-centered and multipole expansion method. And with the combination of the basic Rayleigh-Schrödinger perturbation theory, so we are exploiting the molecular interactions. So for short range interaction, we are using a 6 exponential potential, and dispersive term and repulsive term are taken together in this study. And once for all these interaction energies, whatever we get through these calculations, they are used to calculate they are taken as an input to calculate the probability as well as the different thermodynamic parameters. So this is what I would like to give the picture of different modes of interaction. So if you take this as a flat strip molecule, so let us consider this as a side 1 and side 2, and this is another phase 1, phase 2 as side 1, side 2. And this is the three-dimensional view. Then one of the molecule is fixed in XY plane and the other molecule is shifted into the Z axis. So this is considered as a stacking in mode interaction. Similarly, if the molecule is shifted along Y axis, then it is an in plane mode. And lastly, if the same molecule is shifted along X axis, then it is a terminal mode. So the intermolecular distances, they are chosen in order to keep all the interactions within short and medium range. At the same time, we don't want any van der Waals contacts to occur. So by keeping these 2 points, we are selecting the intermolecular distances for stacking in plane as well as the terminal mode interactions. So these are the model systems I considered. This alkyl cyanobiphenyl systems, which are very famous and which is having a huge past history also. So these molecules are taken into consideration with different homologs. So 1, 2, 3. So this is a propyl cyanobiphenyl. 1, 2, 3, 4, 5 pentyl cyanobiphenyl as well as heptyl cyanobiphenyl. So this is a stacking mode. So we will be considering both the translational as well as rotational motion into consideration. So I'm here presenting the translational data. So in order to save the time of presentation, so rotational pictures are not given, but I'll be giving the briefing of the data. So this is a probability, configurational probability for Y0Z180 configuration. So the meaning of Y0Z180 configuration is that, so initially once for all we fix up the molecule, then the molecule is rotated about Y-axis with 0 degree and with 180 degree along Z-axis. So this is the meaning of the configuration. So, at different temperatures we may calculate the probability, and the picture which is presented here is the probability variation at a clearing temperature, which is 303 point Kelvin for this propyl cyanobiphenyl molecule in ethanol solvent. So the phase 1, phase 2 interactions have been taken into consideration. So for first molecule, the upper one is phase 1, lower one is phase 2. Similarly, for the second molecule out of this pair, this upper molecule is upper side is phase 1, lower side is phase 2. So means here the phase 1 of first molecule is an interaction with phase 2 of the second molecule. So the reverse way also we can consider. So what I mean to say phase 1 here is the first molecule phase 1 is an interaction with the second molecule phase 2. So this is what the meaning. So similarly phase 2. So if you reverse the condition, then the phase 2 of the first molecule will be in interaction with the phase 1 of the second molecule. So this is how we have considered the configuration. So the phase 1 and phase 2 data is presented here, and we will be finding out the almost the particular region which is exhibiting is almost the same probability. So that is found out here in 7 plus or minus 5 angstrom. So means around 2 angstrom to 12 angstrom. Similarly, in DMSO around 20 angstrom to 4 angstrom. So different regions are found out for phase 1, and this phase 1 is decided depending upon the minimum energy configuration. So these regions that will provide regarding the flexibility of the molecules in the particular configuration. Similarly, this is the in-plane mode configuration for Y0 configuration. So the corresponding regions of approximate regions of probabilities are found out in ethanol solvent as well as in DMSO solvent. So with these solvents are selected because one is a polar protic solvent, another one is a polar aprotic solvent, which is having a huge potential for exploiting the different electro-optic applications. Similarly, this is for a CBP5 molecule, bentyl cyanobiphenyl molecule in ethanol, and the corresponding regions are taken into consideration. So this is during the in-plane mode for the same molecule, and these are the approximate probability regions that have been taken into consideration. Similarly, the last molecule, CBP7, the heptyl cyanobiphenyl molecule for a stacking mode as well as the in-plane mode considerations have been taken into consideration for the same configurations in 2 different solvents. And which phase will be more stable, that is identified. Similarly, for this for the same molecule for side 1 and side 2. So here, the terminal mode interactions have been also studied, but I am not presenting here because terminal mode interactions usually they are more significant whenever there is a possibility of hydrogen bonding. So since they are very less significant here in this case, so that's what I have not included the terminal mode interactions. And one more thing, usually in the stacking mode interaction, compared to the in-plane mode interaction, the particular area which is under interaction, that is huge, that is greater. Then comes to the in-plane mode, then comes to the terminal mode. So if you compare 3 modes of interaction, the particular area which is an interaction is higher in stacking, then somewhat lesser in in-plane, then still lesser in terminal mode. So as far as the magnitude is concerned, stacking and in-plane modes, they contribute more for as well as for interaction energy as well as the probability. So in this comparison, we have identified in each case which phase and which side will be more stable for the phase identification. Then this data is used to compute the Helmholtz free energy as well as the entropy for 2 different solvents at room temperature as well as the clearing temperature. And then we have find out the difference of the free energy. Here I have mentioned it is a delta A, which is the Helmholtz free energy. The difference is considered at the clearing temperature to the room temperature. So in some of the cases, the direct values will give us a better picture, and rather than direct values, if you take a difference of the free energy at room temperature to the clearing temperature, that will give us a better picture. So the calculation here, it is shown here. So as far as the negative free energy case is concerned, these values are decreasing. So it is indicating the phase is stable at this particular temperature. And these temperatures are the crystallographic references. So phase 1, phase 2, side 1, side 2, the data is presented for both the solvents. So here we can find out the values to be the very, very lesser in side 1 configuration. So side 1 configuration means that is an in-plane mode. So since it is an in-plane mode, so we are concluding the phase to be the nematic arrangement rather than the smectic. So these molecules do not give the preference to form a layered-like structure, which is a basic characterization for the smectic systems. But this is not a proper authentic conclusion that we can give from the free energy data. So in order to authenticate the result from which is found out from the free energy data, we have calculated the entropy data. Similarly, at room temperature, at clearing temperature, the entropies are calculated and delta S is taken into the consideration, which is the difference of the entropies from the clearing temperature to the room temperature. So here, the data from the entropy, it indicates that the side configurations are exhibiting very, very less entropies. So here also you can observe, here also you can observe, here also, then here also, then everywhere. The side configurations are exhibiting a lesser entropy. So lesser entropy is a more ordering. So since the more ordering is exhibited at in-plane configuration, so the phase is more stable in the in-plane configuration. So the in-plane configuration suggests a nematic structure rather than the smectic structure. So this entropy, we have used the formulas from the probability, which is a quantum approach, and then from the basic thermodynamic formula also. So this is the entropy data from the thermodynamic relation, and this is the data from the probability relation, quantum approach. So these are the entropy data from the quantum approach, and these are the data from the thermodynamic approach. And both the approaches, they are giving the same conclusion. So hence we are finding out a very good agreement between the basic quantum approach and the thermodynamic approach. Obviously, from the data in which solvent it is more stable, that we can easily find out. So this is one method in which one computational procedure by which we can estimate the probable phase of the molecules. So here are the some important points. The various modes of interaction, the stability of a phase that can be identified. At the same time, by comparing the different modes of interaction, we can easily find out the probable phase of the different molecules. And coming to the point of UV visible spectroscopy, so usually in direct view displays, UV light is often used, and this UV light that will cause a gradual degradation of the several liquid crystal molecules. So once the molecule is degraded, the consequent electro-optic effects are altered. So that is why we need to find out the mechanism of the liquid crystal material, as well as we need to search for some molecular structures which can withstand for a longer UV exposure. So this is the ultimate aim of the UV study. So, so if a molecule is that can withstand for a longer UV exposure, so depending upon the absorption wavelength, we can decide whether the molecule is applicable for a wide band gap semiconductor application, or a UV filter application, or a heat resistor application, or some kind of adhesive application, or which kind of application it is suitable, that we can decide. So the progress in this area, it is facing 5 different major issues. The one is the explanation of charge carrier mobility, and the interaction of the UV visible and the near infrared light. And of course, solvent effects are very vital because if you look at the literature, so most of the pure molecules, rather than most of the pure molecules, though the same molecule, if you add a solvent effect, that is showing a better electro-optic property. So that is why solvation models are more important in this case. And to address that solvation model, we need a proper computational strategy. And ultimately, whatever the different wavelengths we are taking into consideration, depending upon the various electronic transitions, we need to tune the absorbing chromophore to match the wavelength for the desired application. So here I have considered the naphthalene-based liquid crystals. So this is a first molecule, and this is a second molecule where we can. This is a naphthalene ester-based liquid crystals, and the crystallographic data is used to construct the molecular geometries. And here the entire structure, based upon the building blocks, we have divided in 3. This is a side group, this is a basic core group, and this is an end group. Similarly, here also we can do the same: side group, core group, end group. So different methods are used: Millikan approach, Laudin approach, and AM1 method, PM3 method, MNDO method, CNDO by S method, INDO by S method. So different methods are used to compute the atomic charges, and then the side group charge is calculated, core group charge is calculated, and end group charge is calculated. So these charges, core group charge, so these are known as a group charges. So core group charge, side group charge, end group charge. So if you look at this, so all the methods are showing very good agreement among the for the estimation of the group charges as well as atomic charges. So if you look at the side group, it is consists of a large positive charge among all. Side group, this consists of a larger positive charge. So end group, this is a very lesser positive charge. So altogether, this is a neutral system, and that's what we need. So here, the meaning of that is that if you compare NaPH1 molecule with NaPH2 molecule, the end group, it consists of a larger positive charge compared to the NaPH1 molecule in all the cases almost. Right? So the end group in NaPH2 molecule, this is a highly positive charge. So to break the bond for NaPH2 molecule, we need a higher temperature. So that is what, depending upon the group charge analysis, we can predict that this second molecule may have a higher transition temperature. And this is an agreement with the crystallographic temperatures which are reported in the literature. So first molecule is having 380.2 Kelvin, and second molecule, this is having 406.1 Kelvin. So the second molecule having a higher transition temperature. So this group charge analysis, this is in good agreement with the transition temperatures reported in the literature. So since these naphthalene-based liquid crystals, they are useful to synthesize or design side chain liquid crystal polymers. And depending upon these temperatures, we can easily understand that these molecules are very, very good in high heat resistance applications as well as the flame retardant applications. And these are the different UV visible absorption spectra of NaPH1 molecule and NaPH2 molecule using three different methods. One is a DFT method, CNDO-based method, and INDO-based method. So different peaks we are getting from this. This is an absorption maxima using DFT method, using INDO-based method, using CNDO-based method. So almost they are very nearer to each other. There is agreement between among the three methods. And as I mentioned in the beginning, in all the direct view displays, the size of the LC module which we use, it generally exceeds a 25 centimeter. So therefore here, these molecules, since they are very lengthy, they are better choice for this kind of objective, as well as for truncating the UV radiation, which is below the 380 nanometer, depending upon the absorption peaks which are achieved using the simulation of the UV spectra. And this is the oscillator strength values depending upon the wavelength. Here you can see the NaPH1 molecule, it is exhibiting the highest peak at around 257.5 nanometer, and NaPH2 around 240.9 nanometer. So we can say that this is a highly photosensitive, for NaPH1 molecule is highly photosensitive because it is exhibiting its highest intense peak at a longer wavelength among these two. And similarly, if you see the last peaks are at around the NaPH1 molecule that is exhibiting around 330 nanometer, and NaPH2 molecule that is exhibiting around 320 nanometer. So if you compare this also, the NaPH1 molecules are highly photosensitive, and these wavelengths they can be selected for the proper photosensitive as well as the electro-optic application. And if you look at this picture once again, so here initially we are getting oscillator strength values to be very, very higher, and later it is getting decreased. So even in the earlier case also, earlier UV spectrum also, initial wavelengths are very, very higher, the extinction coefficients are very, very higher, then later it is being decreased continuously. So these observations include that when the liquid crystal molecules are continuously exposed to the greater wavelengths, there is a continuous decrease in absorption as well as the oscillator strengths. So this indicates that the basic aromatic rings which are present in the liquid crystal molecules, they are getting break with respect to the higher wavelengths. So how far these molecules are stable with respect to the radiation, UV radiation, and how far they are able to sustain, able to exist, and then how far they are able to sensitive with respect to the number of photons intensity, that we can easily understand from these two graphs. And these are the absorption spectra for in benzene system, in benzene solvent, and in chloroform solvent. So obviously we can see the UV visible absorption wavelengths are improved compared to the pure molecules. Then different absorption wavelengths we can see in the visible region also. So therefore here, depending upon these wavelengths, we can consider these molecules for the UV filter applications as well as the photo switching applications also. Because in the case of in the case of different electro-optic applications, UV filters are the more important here. So this is the data I'm presenting for both the molecules in various solvents. So CCl4, C6H6, and then diethyl ether, and then chloroform, then decanol, then water. And fortunately, we got all the values to be somewhat an agreement among the two methods. So different values of oscillator strengths as well as different vertical transition energies are reported here, and homo-LUMO values also are calculated from this. And the homo-LUMO values here, they are suggest depending upon the homo-LUMO, the energy gap values are calculated for NaPH1 system, This is around 7.2 electron volt. For the second system, it is around 7.39 electron volt. So depending upon these values, these are useful for wide bandgap semiconductor applications. And here, one interesting point is that we made a comparison for pure system absorption wavelength to the solvent wavelength. So pure system, pure NaPHE1 system, this is exhibiting its absorption wavelength at 228.71 nanometer, whereas the same system in CCl4, it is exhibiting around 282.62 nanometer. So therefore, there is a shift of 53.91 nanometer. Similarly, in each solvent, the shift is calculated, and the solvent dielectric constant, the shift of wavelength as a function of solvent dielectric constant, that is considered here. And you can find out this here that both the molecules are showing similar trend. And at the same time, the NaPHE2 system, this is showing a greater shift. So depending upon these shifts, and both the molecules are in good agreement with respect to each other. So therefore, with respect to this shift as well as from this data, so we can find out a minimum wavelength, minimum absorption wavelength, and we can find out a larger absorption wavelength. So there is a huge gap. So if you look at the minimum, it is around 206, and if you look at the maximum, that is around 361. So there is a huge gap between the absorption wavelengths for the same molecule. So there is a huge possibility for these systems to use them as a UV filter applications as well as the chemical resistance applications also. So color filter glasses also, color filter applications also can be given from this. And lastly, we can see this here. As I mentioned here, the shift of absorption maxima is taken into consideration. So for the same molecules, both methods show a good agreement. And if you look at this, there is a one particular point where the shift of the absorption maxima is same. So depending upon this value, that may be used for the interference filter. So as the dielectric constant is taken from the very lower value 2.24 to the very higher value 78, we are having a huge range of wavelengths which are exhibited from the two molecules, and therefore we can discuss the highest photosensitivity in various solvents. So this is the significance of the work. So this will, as this is giving huge range of, wide range of UV absorption wavelengths. So this is meeting the demand of the display device architecture. And as I discussed the probable phase of the different molecules, that is giving us the approximate prediction of a phase behavior prior to the synthesis. And since we are searching for a molecular structure that can withstand for longer UV exposure, so that is why this may be treated as a design parameter for the material selection. And of course, as we are getting a huge range of wavelengths, so that is why these molecules are helpful to generate a set of promising candidate compounds. And this is my presentation. Thank you. So now I'm open for questions. If anyone have any question, you can interact with me.
Can I throw a question?
Yes, sir.
Thank you very much. I liked your lecture very much.
Yeah,
so it was excellent. So I will also contact you for some other things later by mail. But I'm just thinking about one thing. For example, with my colleagues, we are interested in electrocaloric effects, and so we would like to have liquid crystals which has the strongest entropy change at isotropic phase to order phase. At the moment, we are, for example, using 12 CB, and the latent heat there is 10 joule per grams. Can you suggest us what liquid crystal which should we use to increase this latent heat change? So at the moment we are using this FCB, and the latent heat is 10 joules per gram. Can you advise us some better liquid crystal with this respect?
Sorry, sir. Actually, I'm unable to get your question clearly, but I think you are asking me a better liquid crystal compound system to have a better latent heat values. Am I right?
Yes.
Sir, usually the better latent heat values, usually I think that depends upon the transition temperature values as well as the particular configuration which is more stable in which solvent. So first of all, as far as my experience is concerned, compared to the pure molecules, the same molecule, if you dissolve in a solvent, then that is showing a better property. So first of all, we need to find out in which solvent that is more stable. I think then only we can proceed for the application for the query which you are asking about. So first of all, we need to find out in which solvent that is more stable.
Thank you very much. I will contact you by email. Thank you.
Sure, sir. Sure. It's my pleasure. I'll be also in touch with you.
Thank you. Very nice lecture.
Hello, Professor Praveen.
Hello, Professor Paul. You're fine and great.
Yes. So nice to see your wonderful presentation. I just curious to know, did you deal with bent core liquid crystal?
Couple of systems we already did some calculation, but they are yet to be published.
Okay, and my question, is it possible, I mean, because I'm working on electro-optical switching of liquid crystals, but theoretically any switching, is it possible to show, I mean, such more simulated patterns for switching, just theoretically?
Right now, I'm working with some nematic dimer systems as well as spectric dimer systems, and we are doing a comparative study on that. Definitely, I'll communicate with you once I get a good result.
Okay. Me and Professor Samu, just now, my colleague is very together working on liquid crystals. So we will contact you definitely because we have a lot of work on theoretical based liquid crystals work. So definitely your contribution will be highly appreciated in near future collaboration.
Sure, Dr. Paul. You are a good friend of mine. You are most welcome. No need to mention, no need to ask me. Anytime a simple WhatsApp message is enough.
Yeah, you are most welcome to be in our conference and nice to see you.
I'm sorry, last time I couldn't make it during my presentation, during that ICN 2021. Reasons are known to you. So I thought this time I should not miss.
Okay. Thank you so much for your coming here and contribute your wonderful presentation. Thank you so much.
Thanks to the entire organizing committee, especially the chairman Tinakaran and convener Professor Paul for giving me this wonderful platform to showcase my results.
Thank you.
Thank you, one and all.
Thank you so much, Dr. Lakshmi, for your presentation. Really impressed your presentation, sir. Thank you so much.
Thank you.
Support our conference. Thank you so much.
All right. Thank you, Dr. P. Lakshmi Praveen, for the amazing presentation, and Dr. L. Anandraj for chairing this session. Ladies and gentlemen, it is now our break session. We will continue the event at 2 p.m. Malaysia time. That's all from me for today. Thank you.